So, dear participants, there is a small request from our side. After the end of the session, please turn off your video so that we are going to take a few screenshots for our reference. So, kindly cooperate in this regards. Thank you, sir.
Welcome, sir.
Hello.
Sir,
Is it
hello, sir.
audible?
Is it audible, sir?
Yes, yes. Hi, Ravi. This is Manohar. Yes, I can hear you.
Okay,
Okay.
okay,
Can
sir.
you hear my voice?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Yeah, fine, fine. Thank you.
So, good evening, everyone. So, welcome to day 4 of our ATAL sponsored faculty development program on innovative green energy generation and storage technologies. I hope you found yesterday's sessions very interesting and are ready for today's exciting topics. Yesterday, Professor Balasubramanian, Professor NIT Trichy, emphasized the importance of various energy storage technologies. So in the second session, Dr. Sridhar, R&D Manager at Amaraja Energy and Mobility Limited, discussed about the advanced materials, components, and management strategies for lead-acid batteries. So today's program includes two compelling and insightful sessions designed to inform and inspire all participants. The first session will focus on advanced energy harvesters. The speaker for this session is Professor Radha Manohar Rao, Department of Mechanical Engineering, Universidad de Chile, San Diego, Chile. His research areas are nanocomposites and functional nanomaterials for energy harvesting and sensor applications. Dr. Radha Manohar Rao will share valuable insights into the advanced energy harvesters today. In the second session, Dr. Balaji, Senior Scientist, ARCI Chennai, will talk about advanced technologies for green hydrogen production. I encourage all the participants to participate actively, interact with the experts, and share your thoughts during the sessions. Let's begin our first session with a warm welcome to Dr. Radha Manohar Rao. He will be sharing his expertise and perspectives on advanced energy harvesters. It's a privilege to have such a distinguished expert with us today to enrich our understanding of this crucial field. Before we begin, I invite our session coordinator, Dr. K. Ravikumar, to introduce today's speaker. Over to you, Dr. Ravikumar, to share more about our distinguished speaker. Thank you.
Thank you, sir. It's my privilege to introduce our esteemed guest speaker today, Dr. Radha Manohar, sir. Dr. Radha Manohar sir is renowned expert in the field of material science and engineering, currently holding the position of assistant professor at that University of Chile, which is ranked 159th rank globally, making it second best university in Chile and ninth rank in Latin America. His research focused on nanocomposites and focused functional nanomaterials is at the forefront of technological advancement. His work on energy harvesting and sensor application, particularly piezoelectric nanogenerators and pressure sensor, has the potential to revolutionize various industries. Dr. Radha Manohar sir, having impressive academic career, includes numerous publications in top-tier journals, book chapters, and patents. His dedication to research is evident in his role as a guest editor for Renewable Energy Journal and his active participation in international conferences and workshops. Beyond his research, Dr. Radha Manohar sir is a passionate educator and mentor. He has successfully guided several undergraduate and postgraduate students, inspiring the next generation of scientists and engineers. Let us extend a warm welcome to Dr. Radha Manohar sir. So, thank you, sir. Thank you so much for accepting our invitation. So, kindly go ahead for the session, sir.
Thank you for the brief introduction. So can I share my
Yes, sir.
yeah. Yeah, can you see my presentation?
Yes, sir.
Yes, sir. Yes, sir.
Yeah, fine, thank you. So firstly, I would like to thank you, the organization committee, especially Professor Shivasham Subramaniam sir and Dr. Ravi Kumar for giving this an opportunity to present my talk in this excellent initiative, FDP program sponsored by ACTE is on innovative green energy generation and storage technologies. So in today's talk, I would like to present on advanced energy harvesters. So their fabrication and properties and applications, which are mostly concerned for various applications for the nano generators and sensing applications. So first of all, thank the organizing this excellent event. So I'm continuing the talk. So before continuing the talk, I would like to give a small brief introduction about the Chile and the my work location as well as my university, so that if the participants who are participating in this event can have an opportunity to extend their research capabilities and research collaboration with the Chilean and other Chilean universities. So, hope everybody knows about Chile. Chile is a country which is located in South America, especially western part of India, very far away from the India, almost 32 hours duration over the flight. And it is the southernmost country in the world, which is closest to the Antarctica and is situated between the Andes Mountains as well as uh, uh, towards the right side, and also to the left side is the Pacific Ocean, east side and west side. So this is a brief introduction about the Chile, and it has various touristic places. Especially we can see in Easter Islands, which we call Isla Pecunia, and also like Patagonia region, which is towards the south of the Chile. And this image you can see here, the Santiago city, which is at the center. So you can see here, like this is the Santiago city, where University of Chile, and we are currently working in this city. Now, about the University of Chile, so already Dr. Ravi Kumar has given a brief introduction. So University of Chile is currently earlier 159. Now currently it is upgraded its ranking to 139 in global QS world ranking, and it is having around 16 faculties. So which is based upon the various groups: agricultural sciences, chemical sciences, and engineering. Especially engineering comes under the faculty of physical and mathematical sciences. So it is over the 16 faculties. We are working on this faculty of physical and mathematical sciences, where various engineering departments are situated: astronomy, physics, geophysics, civil engineering, mining engineering, electrical, mechanical. Total are situated in this faculty of sciences, physics, mathematics. Here the official language is Spanish. So sometimes my talk deviates to the Spanish. Please ignore it. I'll come back to the English again. So we can have a brief intro about the university and Chilean in the following YouTube link. Feel free to ask any questions after the presentation. Also, feel free to contact me anytime. So further collaboration, etc. So we have various funding opportunities in Chile, especially for the postdoctoral fellowships, and also like national doctoral scholarships as well as master's scholarships funded by the Fondesit, and also ENID, Agency of National Investigation Desarrollo, which is the premium funding agency in the Chile. Besides this, there are some university fellowships also available from the University of Chile as well. So to enhance this research opportunities, etc. So now I'm continuing the topic. So about the brief outline of this my talk, FDP program is on advanced energy harvesters, their fabrication, properties and applications. In this outline, I would like to present about the brief introduction about the current energy scenario, as well as the various types of energy harvesters, how it is important to the current energy scenario, especially for the portable electronic devices, and its working principle configurations, especially various types of energy harvesting. We are going to discuss mostly on piezoelectric, triboelectric, and electromagnetic and thermoelectric. So, and also the various materials. Normally, we work on various materials, especially on mechanical energy harvesters. So, like piezoelectric and triboelectric energy harvesting, nano generators, and sensing applications. So, various properties involved in these materials, fascinating materials, and also its sensing applications will be discussed in this talk. So let's come to the quick introduction about the current energy scenario. So you know that according to the current energy scenario, so there is a strong correlation between the development of industrial revolution and also the population. There is a consumption of the fossil fuels. So you can see here 85%, 85% of the energy use over the world is based upon coal, oil, and natural gas. So what happens if there is a depletion of these fossil fuels? However, there are various debates is going on. There might be no depletion of fossil fuels. It can be regenerated. But our concern is to make a sustainable living environment. So to develop an alternative energy resources. So you can see in the graph here, you can see how a 15%, 50%, 15% is only contributed to the renewable energy sources, especially like sun and from the energy from the sun, and also the hydro, and also the solar system. You can see here solar panels. So these are the various 15% of energy consumption is only coming from the renewable energy sources. So among this, the hydro energy is accounted only about 7%. So which is having the solar percentage is only the 4%. So due to the rapid increase of this population and the increasing energy demands, so there is a need of alternative energy devices, and also there is a, as I said, depletion of fossil fuels, fossil reserves. So therefore, a greener technologies can be developed, so which can be used for energy, and it is used for producing, transported, and also the consumption. So there are abundant ambient energy is available in the surroundings. So especially we can harvest energy from the various ambient sources, such as by the physical movements, especially by walking, and also the bending and various physical motions of the human, and also like energy from the sun, water. So these are the various renewable and sustainable energy. If we harvest these energies and can be utilized as an alternative energy sources for, especially for powering low power electronic devices. So however, the energy generation will be by mechanical energy harvesting, especially in this talk we are going to discuss about piezoelectric and triboelectric. So these are low power electronic devices which can able to power. So these low power electronic devices can be utilized without the use of any batteries. So this makes the circuit much simpler, and also there is reducing the electronic components. So if you're using a proper electrical circuiting, converting the alternating current generated from these devices to the direct current. So especially the ambient energy from the surroundings, especially from vibrations and mechanical energies, can be converted into the electrical energy. So these energies can be utilized for powering the various IoT devices. So hope everybody has aware there is a currently research going on IoT based systems like sensors and actuators, etc. Total. So these IoT devices so can be powered by using these ambient energy sources, especially from the human body movements. So the energy can be harvested from the human body movements and can be utilized for biomedical applications and also the smart wearable electronics applications. So these IoT devices can able to transmit the data wirelessly. So and also can be utilized in remote areas, especially to monitor the environmental conditions, also the structural health monitoring. So there the need of an frequent maintenance is required. So these frequent maintenance can be uh, mm, um, can be avoided, prevented by using an self-powered devices. So these are known as like self-powered sensors. So these self-powered sensors can be applied in various applications in structural health monitoring, monitoring the physical movements of the human, especially in self-powered sensor has been widely employed in sensors for see the muscle contraction, pacemakers, implantable devices, etc. So normally the typical energy generated from the human body motions will be around from 0.16 watts to the 11.39 watts. So especially from in the chart, you can see here table, we have presented a typical activity from the blood flow. It can able to generate an electrical energy of about 0.16. So whereas by walking and finger tapping, it can able to generate about 11.39 watts to 1 to 3.2 milliwatts. So these energies can be utilized as an self-powered sensors and also self-powered energy harvesters. So the term energy harvesters, I will clearly more explain about the energy harvesters in terms of nano generators or generators in terms. So it depends upon the various active materials which are incorporated in these energy harvesting devices or nano generators. So currently we are working on various advanced materials in especially for energy harvesting and sensing applications. So these energies can be utilized, can be power up to around the various power ranges from 1 microwatts to 1 terawatts region, and various for portable electronics as well as for industrial applications as well. So I will much focus discussing about this energy harvesting technology utilized for powering these IoT devices, Internet of Things devices. So coming to this energy harvesting technologies, so there are various energy harvesting technologies are available, which are currently much research is going on these energy harvesting technologies, especially harvesting energy from electromagnetic induction and also by piezoelectric phenomena, triboelectric phenomena, photoelectric phenomena, thermoelectric and pyroelectric effects has been widely employed phenomena in these energy harvesting technologies. Currently, we are much focusing on piezoelectric and triboelectric nano generators or energy harvesters, which are based on mechanical energy harvesters. Likewise, various research is also focusing on electromagnetic induction, also harvesting energy from photovoltaic from the sunlight using and various p-type and n-type materials, also a thermoelectric effect, so based upon the p-type and n-type from high temperatures to the low temperatures, and also pyroelectric effect, it also depends upon the polarization caused by the temperatures. So various harvesting technologies can be employed, so one can utilize these phenomena in their respective research to implement their energy harvesting technologies. So our focus mostly on my research expertise is mostly on piezoelectric, triboelectric, and also hybrid energy harvesting devices by integrating some photoactive materials. So especially the photoactive materials from it can harvest energy from the photovoltaic, and this energy harvested from the sun or in sunlight. So it can be enhance the output performance of the mechanical energy harvesters, realizing as an hybrid piezophotonic or tribophotonic energy harvesting devices. Hope you are understanding about various schematic of energy harvesting technologies. Now let's continue more. So as I said, energy harvesters is also called as nano generators. So typically a nano generator is an energy harvester that able to convert a mechanical, thermal and a light energy which is produced by a small physical change in the material. So and it can gives to the electrical output. So as I said, various types of energy harvesting technologies are typically observed in the research: piezoelectric, triboelectric, electromagnetic, and pyroelectric. So, but the term piezoelectric and triboelectric nano generators can convert mechanical energy into the electricity. So, in this presentation, we are much focusing on piezoelectric and triboelectric based materials and its mechanisms to enhance the output and its overall applications. So, as I said, the basic phenomena in the especially like photovoltaic is the energy is coming from the light source, as well as electromagnetic energy is coming from electromagnetic inductions, and it can be used for radio frequency energy harvesting applications, etc. Whereas from the thermal energy can be classified into thermoelectric and pyroelectric phenomena and thermoelectric and pyroelectric nanogenerators. So whereas the kinetic energy caused by the physical movements or also the vibrations and uh, um, coupling of these vibrations with like contact electrifications leads to the piezoelectric and triboelectric electrostatic based phenomena can be employed in this kinetic energy based energy harvesters, whereas especially on we call it as mechanical energy harvesters. So now various materials are employed for fabrication of these nano generators. So it might be a ceramic materials. Everybody knows ceramics are the metal oxides or metal carbides. So it can be employed as an various types of energy harvesters as an active material. So, but these ceramic materials are very brittle and also lack of flexibility. So for overcome this, there are other alternating materials such as polymeric materials, which are very flexible. So well-known polymer material for piezoelectric applications is fluoropolymers. We call it as PVDF, polyvinyl difluoride, which are the fluoropolymers, which is having dipoles and it is a semi-crystalline material, so which is having a ferroelectric polarizations. So I will discuss about the ferroelectric polarization much when we are coming about discussing about various types of materials. So nowadays, to both the individual materials, especially the ceramic materials, metal oxides has higher energy performance than compared to the polymeric materials. So, but as I said, the drawback for ceramics are very brittle and polymers are very flexible. So if we combine these materials, we can able to develop a nano composite materials. As we know, nano composites are the multi-phase materials, so which is having a synergetic effect of both polymers as well as ceramics. You can see here various nano composite configurations are employed, especially on particles are reinforced in the polymeric matrix. So polymeric matrix is a matrix which is the host material, whereas the polymers, whereas the particles, especially nanoparticles or microparticles, which are reinforced into this polymer, which are called as 0,3 types of configuration polymer composites. Likewise, there are other spheres in the polymers, which are called 1,3 configurations, 1,3 which are diced composites, and also the 1,3 also like nano rods which are reinforced into the polymeric matrix. We call it as 1,3 composites. Also there are like laminated composites, which is like also like an functional materials or a functional nano composites, so which are called as a two types of configurations. So these configurations normally a 2D materials, a laminates which are overlapped, and also a sandwiched to make it as an multi-phase materials. So, but which these are like a sandwich. Likewise, there are various types of other structures currently in the aerospace applications. For the lightweight applications, there are like honeycomb structures, so which is lightweight and high strength. This honeycombs typically having a fascinating properties, which is having a lightweight and also low density, and having a strong strength, and also the shear properties as well. So these properties can utilize to enhance the mechanical behavior of the energy harvesters or nano generators. So there are various fabricating routes are available for for the preparation of these nano composite materials for energy harvesting and sensing applications. So you can see here, like especially an electrospinning technique, so where the polarization take place by in situ during the formation of polymer composite materials. This electrospinning technique can be employed for a polymers or a polymer composite materials, and also solution casting routes can be utilized for polymer preparation of polymer composite films, and also hot pressing technique, spin coating technique, tape casting, dicing, and filing are the various fabrication routes for the preparation of nano composites. So now in our research, we mostly focus on preparation of 0322 composites and 13 nano composite based materials by using electrospinning technique and direct mixing, and also a hot pressing and tape casting techniques. Currently, we are using the preparation of electrospinning technique. In this electrospinning technique, so the polymer or a polymer composite solution has been incorporated in a syringe, and this needle of the syringe, which is supplied with an external electrical field, normally at high voltage, which is in the range of kilovolts. So due to the applied voltage, the polymer solution, the fiber has been drawn from this solution, and it is and it deposited on the counter electrode. So mostly we are using as a counter electrode, a aluminum foil or a copper material, where the polymer solution has been drawn due to the due to the formation of Taylor cone structure, and these nanofibers or nano composite fibers are deposited onto this counter electrode. So we can able to get a very thin fibers, which is highly polarized due to the application of higher electric field. Normally, electrospinning technique is widely employed for piezoelectric polymer applications, where piezoelectric polymers require an additional pooling. So use of electrospinning technique can reduce the external pooling. So separately, so normally external pooling can take place by a conventional or a corona pooling that I am going to discuss when I'm briefly discussing about the piezoelectric materials and piezoelectric nano generators. So whereas in direct mixing or a solution casting, this technique can be employed for the preparation of nano composite materials, especially polymer composites, which can be like flexible. But in this, we are not utilizing any electric field. So this can be employed for triboelectric materials for energy harvesting and sensing applications. Whereas when we supply an electric field into these systems, or when we can pole externally by using an electric field, so we can able to fabricate an energy harvester by using solution casting as well. Likewise, there are various other processes, hot pressing, tape casting technique. Now, the thing is, currently there are various advanced techniques are also available, especially many of the researchers you are working on additive manufacturing routes. So especially 3D printing. So 3D printing can be also widely employed to preparation of these various types of nano composite configurations. So recently, I have seen an article which are working on lattice structures. So hope everybody know lattice structures. So coming back to the material science, so there are like body-centered cubic structures, face-centered cubic structures, and simple cubic structures. So these types of lattice structures can be able to can be fabricated by using this additive manufacturing routes by 3D printing. So, and also a composite materials can be prepared by using this 3D printing of polymer nanocomposites. So mostly other 3D printing techniques can also be employed for metallic materials. However, in the current energy harvesting technologies, the metal 3D printing can be utilized only as an conductive layers. So why we need a conductive layer, I will explain in this energy harvesting technology. Now, hope you have clear got an idea about this nano composite fabrication techniques and also the advanced techniques currently which are going on 3D printing technologies. So our projects also currently on the in line with the additive manufacturing techniques that I will discuss at the end of this presentations. Okay. Now, so let us come back to the nano composite materials, especially for piezoelectric applications. So, is well known piezoelectric mechanisms. I hope everybody has known about this piezoelectric mechanism. Piezoelectric is defined as a conversion of electrical energy into the mechanical and also vice versa. So you can see here a piezoelectric material typically consists of a two electrode materials. So the material, the piezoelectric material is sandwiched between two materials. So electrode materials. Now normally the electrode materials might be a copper, silver or a gold, etc. So depend upon the cost effective, we can able to fabricate a piezoelectric energy harvesters. So normally a piezoelectric material which is at rest does not show any output voltage. When this piezoelectric material has been applied pressure or a mechanical deformation, it generates voltage, electrical potential, that is voltage. So due to the deformation of the material. So what happens? Due to the deformation here, a piezoelectric material which is having a non-centrosymmetric structure. A symmetric structure is not utilized for the piezoelectric applications. So it need to have a non-centrosymmetric structure. So what are the symmetric and non-centrosymmetric structure? For example, you can have a cubic structure which is a symmetric structure. So there may not be a polarization, a piezoelectric properties in the cubic structures. If a structure is non-centrosymmetric, non-symmetric, like a tetragonal, monoclinic, there is a capability of harvesting energy by the deformation. And a counter effect is like when we apply a voltage to the piezoelectric material, it can able to undergoes a deformation. So where these materials can be applied as a sensors and energy harvesters and nano generators. So are a sensors and actuators. So actuator is nothing but when we apply a voltage, electrical voltage, the material undergoes deformation. So these actuators can be widely employed in various aerospace applications as well. Similarly, the sensing applications of piezoelectric materials are also widely employed. You can see a typical example of a piezoelectric material for energy harvesting and sensing application is PZT, that is lead zirconate titanate, which is a classical perovskite material. Normally, perovskites are the ceramic materials which is having a piezoelectric and ferroelectric properties. Now, what is like ferroelectric properties? Ferroelectric properties is nothing but a material which is having a spontaneous polarization, even though in the absence of electric field. So due to this spontaneous polarization, so the ferroelectric material can able to polarize the dipoles. So what is a dipole? A dipole is a pair of positive and negative charges. So due to the these ferroelectric materials having a piezoelectric properties. So there is a saying like all the ferroelectric materials can be a piezoelectric, but all the piezoelectric materials cannot be a ferroelectric materials. So the classical example is a zinc oxide material. A zinc oxide is a piezoelectric material, but it is not a ferroelectric material. Of course, there is some slight ferroelectric properties can be reported recently on the zinc oxide based systems. So likewise, there are various polymers also, a piezoelectric polymers, as I said, fluoropolymers, that is PVDF, polyvinyl difluoride, which is an flexible semi-crystalline fluoropolymer, which is having both piezoelectric and ferroelectric properties. So overall, you can see here a piezoelectricity only arises due to the polarization by an external forces. So when it is reverse, it can be applied as an actuator applications. So due to the dipole orientations. So that is the basic mechanism of piezoelectric phenomena. Now, so in this piezoelectric phenomena, the main effect is piezoelectric effect. So the materials undergoes this piezoelectric effect. So this in this piezoelectric materials, a typical constants are mentioned, which are nothing but piezoelectric strain coefficients. That is indicated by Dij. What is Dij? It is a ratio of strain developed in the direction to the J to the applied electric field in I directions. So that is Dij. Some of the piezoelectric strain coefficients are D33, D31, etc. So various materials having this piezoelectric strain coefficients. So here the I direction indicates the polarization direction. That is where we are applying the electric field. So if we are applying in Z direction, that is called a third directions. We call it as a D33. So where the charge is, the polarization is third directions, and the charge is also measured in the third directions. We call it as a D33. And likewise, there are, if you apply an voltage, typically in third direction, the piezoelectric material get polarized in third direction as well. So the electric field is measured by the voltage applied to the time here, and the material was strained along one direction, and it is the strain estimation can be especially in the piezoelectric matrix coefficients, we can use a compliance matrix. We call it as the strain developed in one direction is nothing but change in length to that in the direction to the x-axis or the direction towards the one to the original length. So a typical strain developed in a piezoelectric material in one direction is nothing but D31 voltage per time. So where D31 is a polarization here in third direction and the measured charge in one direction. So that is the piezoelectric coefficients D31. Likewise, there are other piezoelectric coefficients which is need to be investigated for the piezoelectric materials, which are known as piezoelectric stress constants, which is indicated by E31 in some terminology, which is they are using some other terminology gamma, where D31 and the Young's modulus gives the piezoelectric stress constant, where Y is known as Young's modulus. Normally, a typical Young's modulus is varying for the ceramic and polymeric materials. So polymers which is having a low Young's modulus, however, there is an low strength material, but it is having an excellent flexible properties, can be applied for then flexible electronic applications. So likewise, there are other piezoelectric coefficients known as piezoelectric voltage constant, that is indicated by Gij. So that is same, the terminology I and J, that is the polarization and also the measure the charge. So that is the piezoelectric voltage constant. This is indicated by V is equal to G31 into F by the working distance you can see here, where F is nothing but the force applied. So that is what, and the width of the material. Now you can see here, there are various piezoelectric principal configurations employed, especially for the fabrication of nano generators or energy harvesters. So we call it as a piezoelectric material, especially from PZT. So PZT is nothing but here is a lead zirconate titanate material. So it is a lead-based materials. So lead-based materials are also toxic. So currently considering the sustainability, much research is focusing on lead-free based materials. So these piezoelectric materials, which is having in two modes, one is a resonance mode and is a non-resonant mode. In resonant mode, for example, a typical piezoelectric applications, you can see a cantilever. So where the cantilever oscillates under the excitation of an electrical force. So the electrical force is applied at the tip of the cantilever of the PZT, and the piezoelectric layer deforms and it is generated an electrical potential. In the non-resonant mode, a symbol like a piezoelectric device, So it's a structure where a piezoelectric is stacked, sandwiched by the top and bottom metal caps. So which is like a symbol-like structure. So where we are applying force, it can able to generate an electrical potential under the non-resonant mode. So due to the frequency applying a dynamic conditions also, the mechanical force, we can able to measure the piezoelectric response under the non-resonant mode. Whereas in resonant mode, we are applying an excitation external force. Also, this can be employed as an hybrid energy harvesters when we are combining with the electromagnetic field. So where this electromagnetic field, when we apply a load at the magnet at the tip of the cantilever, so due to the electric field, there is an oscillations in the cantilever beam caused by the magnetic field, and the element can be able to generate the electrical voltage. So various energy constants are reported for the piezoelectric materials. So PMN, PT, PZT, and also PZT based thin films, polycrystalline materials, which is having a higher piezoelectric strain constants, that is D33. So that is around, especially PM and PT has been reported around single crystalline material, which is having a 2000 to 3000 piezoelectric strain constant. Whereas in lead-free materials, especially perovskite materials, as I said, PZT, BiTiO3, which are the AbO3 type structures, where A and B are typical cations and oxygen atoms. This is a typical perovskite structure. Normally, first perovskite materials are named after the preparation of a calcium titanate. So it's a typical perovskite material. So thereafter various perovskite material has been derived. Currently, there are much research is also going on metal halide perovskites. So that is cesium lead bromides, that is halogens. So these are having a piezoelectric properties as well, also a photoactive properties. So therefore, it can be able to employ in piezophotonic applications. And other materials like non-ferroelectric materials, perovskites are the ferroelectric materials, are also piezoelectric materials, and other materials such as zinc oxide, which is easy to prepare, and various forms can be prepared like rod-like structures, hollow-like structures, and flake-like structures. Flower-like structures can be prepared by using various solvothermal route or hydrothermal routes, and also sol gel techniques. So, but it is having a lower piezoelectric constants. So, whereas zinc oxide-based materials has been widely employed in energy harvesting and sensing applications as well. Apart from it is having a property known as wide bandgap semiconducting material. It can also employed as in gas sensing applications and photocatalysis, piezo-catalysis applications as well. So there are other materials, especially polymers, which I said PVDF is a fluoropolymer, which is having a D33 of negative. You can see it, negative constants. So therefore, we can able to prepare a composite films by using a PZT, that is lead-based ceramics, and also a PVDF, a fluoropolymer, and it can enhance the piezoelectric voltage up to 13 to 25 positive, that is D33 strain constants is positive, especially in the composite materials. So these are the typical various piezoelectric materials. However, now much research is going on various advanced materials, especially mexins, we call it as, which are derived from max phase materials, graphene-based systems, and also the gallium nitride, aluminum nitride, which are the various piezoelectric materials are reporting for energy harvesting and sensing applications. Now, I can show here typically this is one of our recent published article for piezoelectric energy harvesting capabilities, especially in lead-free PVDF, BCT, BJT composites. As I said earlier, a PZT is a lead zirconate titanate. It is a lead-based material. So utilizing lead is a toxic, and also it is hazardous to the environment. So much we focused on a lead-free based perovskite material, that is BCT, BJT. So BCT BJT is nothing but barium calcinate titanate and barium zirconate titanate composites, which are developed by reinforcing into the PVDF matrix. So here we have developed a flexible mechanical energy harvesters by integrating these nanostructures, that is BCT BJT, into the polymeric matrix, that is PVDF matrix, by using a solution casting route. Here, the BCT BJT nanostructures are prepared by using an typical sol gel technique. So, for the preparation of these perovskite materials, and then normal solvent casting has been employed to preparation of a flexible composite films with varying concentration of fillers, that is BCT BJT nanostructures. And you can see here a typical SEM images of a pure PVDF and various concentrations from 5% and 10%, 20%, 30%, ABC, B, C, and D are various concentrations of nanofillers or BCD, BJT nanostructures. So into the polymeric matrix. So, and we have thereafter we studied the composite films for the dielectric properties. So you can see the dielectric properties were significantly enhanced in comparison with PVDF. So here at lower frequencies, the dielectric constants are typically higher. So what is dielectric constant is nothing but we have measured a real permittivity. So that is it tells about the energy storage capability in the material. So at low frequency we have higher dielectric constants, which increasing the frequency, the dielectric properties, that is permittivity, has been decreasing. So what is the reason? At higher frequencies, the dipoles do not have much time to polarize. So, but at lower frequency, the dipoles have much time to polarize with respect to the applied electric field. Here we are applying an AC voltage. So AC voltage is like alternating voltage, so positive and negative, so that the dipoles in the material so undergoes polarization with different directions, that is positive and negative directions. So there is a flipping of dipoles has been observed in when we are applying an AC field. So therefore, at higher frequencies, we have very less time, so that the dipoles cannot be oriented, and therefore the polarization is decreasing at higher frequency, which leads to the lower dielectric properties. So normally these energy harvesting materials or nano generating materials should have low dielectric losses. So the dielectric losses is nothing but tan delta losses, which is nothing but decimation caused by the heat or other electrical losses. So typically the losses should be less than 1. So if it is less than 1, the material have a charge storage capability. So thereafter we have fabricated an nano generator based energy harvester, which can be also used as a sensor, where the polymer composite, that is PVDF, BCT, BJT nano composite, has been sandwiched between a conductive layers. Here the conductive layers we have employed is a silver layer and both the sides. And these silver layers we have taken electrical contacts, and it is encapsulated with a PET, that is polyethylene terephthalate, to make it much robust for the mechanical energy harvesters, because we are applying a mechanical force. So we need to observe these shocks, and the material should be able to observe this mechanical energy, and it can able to enhance the output voltage. So we can, and thereafter we have measured the composite films at various mechanical tapping. So we can see for the composite films with 10%, 20%, and 30%. So in this typical composites, around 20%, we have had higher output performance, that is higher voltage, that is about 11 volts has been achieved under the mechanical force, where the dielectric constant of the material is around 40. And thereafter, various human body motions, that is wrist bending, elbow bending, knee bending. So we have observed an output voltage of about 1.4 volts to 2 volts, that is a peak to peak voltage. So but the energy generated here is like an AC voltage. So normally when we are employing for any practical applications, we need to rectify this AC voltage into the DC voltage by using a bridge rectifier circuits, and we can able to employ for portable electronic applications, and also we can able to store this energy by using a supercapacitor or an capacitor. So and we can able to harvest this energy, and we can employ for various other practical applications by minimizing the usage of a battery. In this special research, we have tried to harvest energy. So we have made a prototype to harvest energy by a water droplets, like a typical rain energy harvesting. So we have a typical laboratory experiment has been conducted on this nano composite. So where we have various water droplets by using a burette at different flow rate. We have incorporated various droplets, and we have observed the output performance by using an oscilloscope. So normally oscilloscope with the ends are connected to a single channel oscilloscope, and we have measured the out peak to peak voltages. Here by the water droplets at a particular specific height, we have achieved an voltage about 1.5 to 2 volts, the peak to peak voltage under the water droplets. So therefore this can be employed as a rain energy harvesting application as well, if we are utilizing for a large scale from laboratory scale to the large scale applications. So this is one of the where research has been published in Ceramic International recently. Yeah. Now, also now you can see here, there is nothing but another piezoelectric nano generator, as I said, which can able to harvest energy by converting the kinetic energy into the electrical energy by the action of any active material, that is a nanostructured material. As I said, zinc oxide is a fascinating semiconducting wide band gap semiconducting material, can be employed as an piezoelectric nanogenerators. So much research has been published on this zinc oxide based piezoelectric nanogenerator. So in this, the zinc oxide nanostructure has been grown on typical polystyrene substrate, and it is sandwiched between an electrodes. And you can see here the zinc oxide has been grown on this polystyrene substrate. So this zinc oxide nanowire textured film on the polystyrene polymer substrate, so can be used as a flexible polymer composite, which is using a low cost organic material for the fabrication of piezoelectric nanogenerator. When under the various mechanical conditions like bending and compressing, so you can see here an output voltage of about 10 volts with an output current about 0.6 microamperes with a power density of about 10 milliwatts per centimeter cube has been achieved on this zinc oxide based energy harvesters. So this motivated us to publish our article, especially on zinc oxide based systems. Earlier we work on zinc oxide based sensing materials. So later on we have tried to move on make a polymer zinc oxide nanocomposites by using an electrospinning technique. So that is the currently work is undergoing on. So an electrospinning fibers, polymer fibers has been fabricated by reinforcing zinc oxide nanostructures into this polymeric matrix. And we have studied the structural properties by using X-ray diffraction. The material is having an beta phase. Normally, beta phase is a polar phase is required for the polymeric materials. If it is a non-polar phase, the metal may not show the piezoelectric properties. And if it is a polar phase, that is beta phase. So polar phase, non-polar phase, nothing but beta and alpha phases in the fluoropolymers. So where the material should having a beta phase, which is having a polar phase. And we also studied the dielectric properties with respect to the applied electric field, and the composite of zinc oxide with the 10% shows a typical higher dielectric constants and higher permittivity with respect to the AC voltage under the frequency of about 10 hertz to the 10 megahertz. So as usual, at lower frequencies, the dielectric constant is very higher compared to higher frequencies. So this is due to the typical polarization mechanism. We call it as MWS polarization. What is MWS polarization? which is term known as Maxwell-Wagner-Siller polarization mechanism, which is says about the space charge polarization typically at lower frequencies and the dipole polarization at higher frequencies. And we have measured the output voltage and current under a load resistance of about 1 mega ohms for just only the 1 weight percentage of zinc oxide. So other studies has been under progress for the preparation of higher concentration of zinc oxide nanostructures. So the maximum average output current for 1% weight percent zinc oxide is around 1 microamperes with a load resistance of 1 megavolts. And an output voltage has been achieved about 1.2 volts, which is an AC current. So later on we can rectify it by using a bridge rectifier. Now, quickly, just focusing on other piezoelectric nanogenerator based on flexible piezoelectric nanogenerator, where they have employed recently published in ACS applied materials interfaces, where they have employed bismuth ferrite particles. So what are the properties of bismuth ferrite? It is showing a magnetic behavior. So these magnetic particles has been reinforced into the polymeric matrix. Here the polymeric matrix is a PDMS. It is a polymethoxy disilane, so which is a transparent elastomer. So where the bismuth ferrite particles has been reinforced by using a spin coating technique, and it is sandwiched between the electrode layers. So this can, as bismuth ferrite, it is also an AbO3 structure. It can also show a piezoelectric properties as well. Also shows a magnetic properties. Therefore, these studies can be employed in future as a piezoelectric and electromagnetic hybrid energy harvesters. So you can see a typical flexibility of the composite films has been shown, and the bismuth ferrite and PDMS structures has been sandwiched between the aluminum electrodes. The most important thing is the particles should be homogeneously dispersed, especially in the case of piezoelectric nanogenerators. If it is a non-homogeneous, there might be an agglomeration. Due to this agglomeration, there is segregation of particles, which decrease the properties of the piezoelectrics, and also the undergoes a plasmoic resonance can be developed into this in the dielectric properties of these piezoelectric nanocomposites. Here, typically they have prepared about 40 weight percentage of bismuth ferrite has been reinforced into the polymeric matrix and studied the piezoelectric performance under various pooling conditions. So let me explain now about the pooling conditions. So what is pooling? So pooling is nothing but normally employed for the ferroelectric materials. So especially bismuth ferrite is also a ferroelectric and ferromagnetic materials, where the pooling conditions is normally carried out under conventional pooling or a corona pooling. So in the conventional pooling, where we are applying a high voltage, where the materials undergoes polarization under the atmosphere temperature, higher temperatures. So due to this strong orientation of these dipoles has been observed, this leads to the piezoelectric properties. So normally a conversion of these ferroelectric properties to the piezoelectric properties, a pooling, electrical pooling need to be carried out. So either I said conventional pooling. Normally this conventional pooling is being carried out under a silicon oil, where the material, composite material or a ceramic material has been applied in high voltage, that is in kilovolts, so to polarize the material. So whereas the drawback of this conventional pooling is nothing but there is a contacts, and due to this contacts under an high voltage, there may be a failure in the material due to the dielectric breakdown. So to overcome this, so there is an corona pooling technique. There is an non-contacts where we are placing our material, ferroelectric material, in the electric field, and we are going to apply an high voltage and high temperatures, so the materials can be polarized without any contact, so that this leads to the prevention of failure of the material, especially polymer materials, which can undergo punctures so under a high voltage. So this can be minimized by applying an corona pooling or a non-contact pooling, we call it as. So you can see here after pooling and before pooling how the dipole orientation, you can see before pooling the dipoles are randomly oriented. When we are applying an electric field, so the dipoles are aligned. So due to these alignments, it can able to show higher output performance of the piezoelectric PDMS and bismuth ferrite composites. So you can see an 10% has shown lower output voltage and 40% shows higher output voltage, around 4 peak to peak voltage has been achieved in these types of composite films. And further, there is a rectifying circuit has been employed, and we can able to charge an LED by using this nano composite PVDF and bismuth ferrite and other reinforcing materials. So, and also we can rectify the circuits, and the AC voltage can be converted into DC and to enhance the voltage. However, the AC peak to peak voltage will be lesser than the DC voltage due to the various other electrode effects, and also there is a electrode losses that is caused by the diodes, rectifying use of rectifying diodes, etc. So and then output voltage can be applied. So these 2 to 3 volts can be charged on various capacitors. In the figure D, you can see here a various capacitors. 1 microfarad, 2.2 microfarad, 4.7 microfarad has been charged by frequency mechanical tapping, and this charged capacitor can be utilized for various powering LEDs or any other power electronic devices. So likewise, the active materials, so which are mostly responsible for this piezoelectric properties. So here there is another various types of structures which are reported recently, which is like rectangular, triangular, and S-type structures. So the typical structures make the devices much deformation. Due to this deformation, there undergoes an excitation under a proof mass of load, or it may be a magnetic particles which can excite the materials by the action of electromagnetic and also piezoelectric, can enhance the piezoelectric performance of these devices. So this is one of the typical reported article obtained from the literature. And apart from this, we have fabricated an hybrid composite. So that is utilizing an zinc oxide based material. The surface of the zinc oxide materials, if we modify the surface by a conductive fillers, that is carbon based materials, so which can improve the dielectric properties. So you can see here a frequency dependent dielectric studies has been carried out for this polymer and uh, zinc oxide modified with carbon. So you can see a higher permittivity, about in 100 heads we have achieved about 125, with a reinforcing efficiency about 28 percentage with respect to modified and unmodified nano composite, you can see. So here we have mentioned a microcapacitor model to enhance the dielectric properties. Whereas, especially when we modify the surface of the zinc oxide, we have proposed a model known as pseudo microcapacitor model. So, in these pseudo microcapacitor models, uh, it can enhance the dielectric properties as well as output piezoelectric properties, and also the change in capacitance of the this polymer composite materials. So, you can see here under various pooling conditions, before pooling and after pooling, when we apply a voltage mechanical deformation in the material, we have observed a change in capacitance. So change in capacitance with respect to different loading conditions. So you can see here different loading conditions when we applied about 0.65 kilopascals, like just like a manual tapping, and 1 kilopascals and 2 kilopascals. So at the modified surface, and you can show higher change in capacitance in comparison with unmodified hollow zinc oxide structures. And also these structures can be also subjected for various bending conditions at different bending angles from 0 to 80 degrees. By manual bending, we have observed the change in capacitance of this nano generator based sensor. So this is the work published in Journal of Physical Chemistry C, one of the previous work during my doctoral studies, and which is showing an excellent material for an capacitive sensing as well as piezoelectric nano generator application as well. Now the same material we are trying for triboelectric applications. Now that I'm going to discuss in the coming slides about the triboelectric mechanism as well. I need to run very fast, so I have half an hour remaining. So now, likewise, there are various piezoelectric properties has been employed with various morphologies. So the morphology, it might be a nanorod-like structures, nanofibers like type structures, and also a nano wires with lead-free based materials. So various material has been reported recently, and performance of these piezoelectric nano generators has been reported. OCV is nothing but open circuit voltage, and SCC is nothing but short circuit current. These are the basic electrical measurements that need to be studied if one who are investigating the piezoelectric properties or a triboelectric properties of a nanocomposite or a polymers or a ceramic nanostructures. So apart from the directory properties of the material. So you can see here one of the various applications of the piezoelectric energy harvesting systems as well as sensors. It has widely employed in biosensors, human body energy harvesting, and also in tissue engineering, cell stimulus, especially in the skin. Artificial skin also can be employed as an wearable electronics can be employed, implantable devices as a pacemakers, and also we can able to use the piezoelectric energy harvesters for monitor the structural vibrations, condition monitoring, as well as also harvest energy from the road by using the frequent movements of the automobiles, and also the due to the walking movements, the piezoelectric crystals can also incorporated into the shoes, so it can able to generate the voltage, and you can be able to charge that low power electronic devices like smartwatches and various other, minimizing the usage of batteries. So that's the typical one we are using. And the other work recently published is on metal halide perovskites. As I said, cesium lead bromide, it is a highly fluorescent material. So when are intercalated with zinc oxide material, as I already showed, zinc oxide is showing excellent piezoelectric properties. When we intercalate with this metal halide perovskites, the zinc oxide like a quantum dots here, which are decorated on the surface of these halide perovskites, that is cesium lead bromide, and it can shows that enhanced crystalline structure, showing an orthorhombic structure for the perovskite materials, and the hybrid, it is shows the presence of zinc oxide, and we have measured the structural characterization by using X-ray diffraction, microstructure characterizations, and the typical size of an hybrid nanostructures are around 300 nanometers, and also in zinc oxide nanostructures are typically 10 nanometers. And thereafter, we measure the dielectric properties of these hybrid nanostructures by measuring the frequency-dependent dielectric properties. And also, we have measured the output current with respect to the voltage under an illumination condition, that is dark and light conditions. So these hybrid nanostructures under when we illuminated a light, it was normally a sunlight, so it is shown like enhanced output current, that is a photo current. So under light conditions and in dark conditions, the photo current has been reduced. So this can be employed as an piezo photonic energy harvesters that I'm showing in this picture. You can see here a typical energy harvesting nano generator as a self-powered sensors. So here a self-powered photo detector, we call it as a photo detector, where the hybrid nanostructures has been deposited on an electrode surfaces, and normally this photo detector requires a bias voltage. How we can give a bias voltage? Normally a battery source or an external voltage. So to minimize this batteries and giving an external bias voltage, we are using an energy harvesting device, that is a piezoelectric zinc oxide and polymer structure can under mechanical tapping, it can able to generate the energy. So this generated energy can be charged in a capacitor, and this capacitor can be utilized connected to an photo detector to make it as a self-powered sensors. So that is a typical work has been published also in Journal of Physical Chemistry say, in the year 2018. And this is one of our postdoctoral project in funded by government of Chile. Now, till now we have discussed about piezoelectric nanogenerators and energy harvesters. Now I'm going to discuss about the what we call like triboelectric nanogenerators. So here the triboelectric nanogenerators is nothing but an energy harvesting device that converts the external mechanical energy into an electrical energy by the triboelectric effects and the electrostatic induction. So as it is, which is clearly nothing but which converts mechanical energy into the electricity through the triboelectric effect and electrostatic induction. So this is a recent research, especially published, much discovered in 2012, and much research is focusing. And the output performance of this triboelectric nanogenerator or an energy harvester is typically higher than the piezoelectric nanogenerators. Here, due to the contact electrification, so there is a separation between the two layers. Normally, we are having in this triboelectric energy harvester nanogenerators, we are having a two dissimilar materials which is having an opposite polarity. So one is like positive, one is negative. When it comes in contact and it is separated, there is a charges are generated. Due to these charges, when we corrected these charges by using an external circuit, the output power is much higher than compared to piezoelectric energy harvesters. So this is produced by, as I said, a contact separation or a relative sliding between the two materials due to the friction developed between the polarities of dissimilar materials. So where you can see the typical triboelectric performance, that is sigma is nothing but sigma d by epsilon, where sigma is the triboelectric charge density and d is the interlayer distance, that is the distance between the two layers, and epsilon is the permittivity of the materials. Same, here also the triboelectric materials, we are using a dielectric materials, also a ferroelectric materials, but not the conducting materials. Conducting materials is only employed as an electrode layers. So various flexible triboelectric nanogenerators has been introduced, which is like an alternative method for piezoelectric energy harvesting, and which can able to employ harvest energy from the ambient mechanical energy sources from the surroundings as well. So here there are various working modes of this triboelectric nanogenerators. So I think I have a time more. Yeah. Now, so that is like contact separation mode, sliding mode, and a freestanding mode with double electrodes. So, and also contact separation mode with single electrodes. So, and single electrode and sliding mode also, various working modes, and also freestanding mode. So, but currently we are mostly working on contact separation between single electrode and also double electrodes. So, in other depends upon the laboratory facilities available. So, just like under mechanical dynamic conditions, so we can able to get an contact separation mode by using a dynamic shaker, applying in any vibrations laboratory you can employ. In sliding mode, we need to have like a reciprocating devices to have to develop a friction between the during the sliding. So these are the various working modes of the triboelectric nanogenerators. So it is much easy. Only the thing is we need to make a materials which is having a dissimilar polarities, that is opposite polarities. So as I said, this triboelectric layers, various triboelectric layers has been employed. You can see in the picture, human skin, glass, nylon, which are the positive, typical positive tribopositive layers, whereas the negative layers is nothing but fluoropolymers, as I explained, PVDF, and polyvinyl chloride, polyamide sheets, and polyester are the negative triboelectric layers. And you can see the typical the working mode of contact separation under pressing, releasing, how the charges has been generated. This is the working mechanism of triboelectric nanogenerators based upon triboelectric charging on the surface, and also the electrostatic induction that that helps to the flow of the current. So by using two dissimilar materials. Here the two dissimilar materials which is having a opposite polarity. So that is shown here in the typical structure, that is negative polarity and the positive polarity. And you can also have when they are when these two surfaces are separated, so the charges are compensating and there is a charges are built up on the top and bottom electrodes due to the electrostatic induction, which employs the promotion of electrical flow due to the accumulation of charges carriers, and thereafter it can be neutralized under releasing, and finally once again when it is pressing under dynamic. This is a repeating cycle, so where the energy can be harvested by the continuous contact separation modes. So you can this is one of the recent good typical basic article which can explains about the triboelectric layers and its working mechanisms. So these triboelectric nanogenerators can be widely employed for wearable electronics applications, especially for powering the electronics with microwatts to the especially in smart lens and also smart glasses where we need a power of about in the scale of watt regions. So these triboelectric nanogenerators typically having an layered structures. So if we modify the structures by using an micro pattern structures and also a specific design structures, that is multi-layer zigzag structures and also a surface structures and also a planar type structures, various structures can give various output performance. Now, as I said, advanced fabrication route by using 3D printing, we can able to prepare a lattice structures so that the surface of the triboelectric layers has been charged up and it can be able to give the higher output performance. Normally, the output performance of the triboelectric generators can be measured by measuring the power density and energy density. So well known, the power density refers to the amount of power generated per unit area, whereas for the if the modifying the surface, it can able to give the higher power density. So whereas energy density is nothing but the total electrical energy is generated and stored in unit area or a unit volume. So when we compare with smooth surfaces, the micro pattern or a zigzag structures or a specifically designed structures can have an higher output performance. So you can see here a micro pattern structure typically shown about 2.34 microwatts per centimeter square. It is a power density, and a nanoparticle with textured, so TG structure, which is having separated with an spacers, that is spring loading, so which is showing about 31.3 milliwatts per centimeter square. So these are typical various application of triboelectric. The basic challenges in this triboelectric nanogenerator is nothing but, so normally this works on the Maxwell displacements. So as you know that from the Maxwell displacement current, the output of the triboelectric nanogenerators is related to the different materials. So especially for permittivity and triboelectric charge density and the surface morphology are the various parameters that can be gives the Maxwell displacement current. So if you modify the surface charges and modify the properties of the dielectric properties of these triboelectric layers, we can able to enhance the output performance. So here I'm running fast. So typically you can see a polystyrene layer which is having a nanowires of PVDF, and polystyrene with PVDF shows higher output performance and also slight incorporation of about carbon nanotubes, so which enhanced the output performance 11 times when compared to with a pure PVDF. So this typical charge density can be enhanced if we are improving the charge densities in the typical composite materials. And also you can see recently the other work adding in mexins. Mexins are the 2D materials similar like in graphene based materials, when we incorporate this mixin into this polymeric matrix, that is PVDF, with a different weight percentage, 10, 20, and 15 and 25. So the dielectric properties has been increased at higher concentration, up to 25 weight percentage. So this composite can be utilized for tribolotic nanogenerators. And for the here you can see simple structure has been fabricated by using a copper and a copper as an electrodes, and a nylon is a tribopositive layer, and a PVDF mixin as a tribonegative layer. So, and by converting the AC to DC by using a bridge rectifier, and we can see several LEDs, red LEDs has been glowed under the mechanical pressure by manual tapping. So you can see an enhanced output open circuit voltage up to more than about 400 voltage can be generated by using this PVDF MX in composites. So, and also at different load conditions, 1 newtons to 50 newtons with increasing the load. So you can see here the enhancement in the output voltage, open circuit voltage of the composite PVDF and mix in tribolotic nanogenerators under various loading. And also a charges has been measured, measuring the charge density in nanocoulombs at a typical composition at various loading conditions. So that is one work recently, and another work here they have used like barium titanate based PDMS composite films. So here the piezoelectric and triboelectric nanogenerators phenomena has been explained, making it as an hybrid energy harvesting devices, which is having a dual effects. So in comparison with piezoelectric and triboelectric, it can shows higher outputs by using reinforcing a barium titanate, which is a piezoelectric material, and PDMS is a flexible elastomer. So, but having a contact separation is a triboelectric phenomena, and the piezoelectric phenomena induced in the barium titanate can enhance the output voltage. So, and they have measured under various pooling conditions in forward pooling and reverse pooling. The pooling is, as I said, explained when we are applying a voltage up to 12 volts. It's like 12 kilovolts. So, the forward pooling conditions and the reverse pooling conditions, that is, we are reversing the field, and we are enhancing the output performance, especially.
2 minutes, there is a small technical problem.
Dear participants, please be on hold. There is a small interruption due to uninterrupted internet connection. So, sir will rejoin again. So, please be on hold. సార్ ఏమైంది సార్?
ఏం కొద్దిగా మరి నెట్వర్క్ ఏమో మరి నాట్ కనెక్టింగ్ వస్తుంది.
అవునా సార్, యాక్చువల్గా మీరు మొబైల్ నుంచి ఒక పని చేయండి సార్. మోస్ట్లీ సెషన్ అయిపోయింది, ఆల్మోస్ట్ అయిపోయింది కాబట్టి క్వశ్చన్ అండ్ ఇంటరాక్షన్ సెషన్కి వచ్చింది సార్. లేదంటే మొబైల్ నుంచి అయినా.
ఓకే ఓకే
ఒక ల్యాప్టాప్ కనెక్ట్ అవ్వకపోతే మీరు మొబైల్ నుంచి అయినా వచ్చేయండి సార్.
వన్ సెకండ్.
ఓకే సార్. So, dear participant, there is a small internet issue. So, Sir will rejoin in the session. Kindly, be there in the session link.
Okay, sir. Sir joined already. Please.
Yeah, now I think there is
Fine.
some disconnection. I hope it's like running out of time. So let us, I will summarize it, and we can quickly go for question and answer session.
Dear participants, is there any queries from your side? Please feel free to ask to Sir. Sir will be in line. Is there any queries from audience side?
So we are running out of time, so just I am skipping the thermoelectric performance and electromagnetic based energy harvesters. The research also has been going on. If someone interested, you can work on these types of areas as well. Magnetic based energy harvesters and thermoelectric based energy harvesters. So we can measure the thermoelectric performance and various applications as well. Pyroelectric based energy harvesters, which is undergo due to the polarization by the temperature. So this is some of the work. And also integrating this hybrid energy harvesters is also a fascinating research can be employed. Yeah. Any questions?
Dear participants, if you have any questions, please raise your hand or you can post in the chat box.
Yeah.
Sir, there is some queries in the chat box. So kindly check it, sir.
Yes. I'm saying. So there is a question from Dr. Shiva Jagadish. What kind of energy harvesters are using for textile materials? Normally for the textile materials, mostly like piezoelectric nano generators or energy harvesters, piezoelectric materials, especially they are using like a natural materials, especially natural polymers like silk is a natural polymer, nylon is a natural polymer. So in these natural materials, they are going to incorporate some nanoparticles, especially maybe zinc oxide and the other types of materials. So to make it like a piezoelectric energy harvesters. Also, in a triboelectric, by with small spacers, we can able to develop with the structures, as I explained earlier, with the various uh, micro pattern structures, we can able to develop in a textile. So normally, nylon is a tribo positive layer, and a polymer, a PVDF, a fluoropolymer is an tribo negative layer. So with this can be also employed as an in textile materials to make it as an wearable electronic devices like textiles, etc. So mostly piezoelectric and triboelectric energy harvesters can be employed for in textile applications. And the other question is from piezoelectric energy harvester for solar bricks through lights. I did not understand the question. That is like piezoelectric energy harvester for solar bricks. So I did not understood. So what does this mean? Like yes, but the thing is, in solar bricks, we can incorporate the piezoelectric crystals. So that also as the solar bricks, it can be also like an thermoelectric as well, and also like piezo. So in this solar bricks undergoes vibrations. So this piezoelectric crystals undergoes vibrations. It can able to generate the voltage. So it can also employed as a good idea as a prototypes. Solar bricks can be developed. That we can say like piezo solar bricks. So that will be very good for technology readiness level project, especially directly in civil construction applications. And what else? Any other questions? Sir, okay, there is a question from Dr. Nagaraju. That is, sir, can we adapt these materials to design thermal comfort suit? Yes, these type, it depends upon finally the active material, especially for the, as you are saying, thermal comfort suits. You can employ a thermoelectric materials or a pyroelectric materials. So based upon this, we can able to measure, we can able to fabricate a thermal comfort suit also. So it can be employed for various smart materials. For it can able to generate the energy from the thermoelectric effects. Still, there is lots of these are the main questions typical from the participants and other things. Well, thanks for the compliments and everything. Yeah, Ravi, can you please?
Yes, sir. Actually, sir, here most of the participants are PhD holders. So, can you
Yeah.
share your thoughts? What are that funding opportunities are there in the Chile? And if you want to do any postdoctoral fellowships, how to approach it? Can you give
Yeah.
small intro?
Sure, definitely. So actually, there are various funding opportunities. So before coming to these things, I would like to explain a small our recent work, which is funded by the Chilean government agency, that is a foundation initiation project, which is an hybrid nano generator based multifunction sensor. So this is a project which is funded by Fondesit, ANID, Agency of National Investigation Desarrollo. So there are various funding opportunities. This is a recently awarded project, so which is on 3D printed structure. I'm not disclosing much on materials, but some researchers working in our laboratory, they are working on this piezo phototronic nano generator as well as triboelectric nano generators. So basically, under my group, we have like funding opportunities, especially in this type of energy harvesting applications. We can write a proposals and submit to the funding agency, and there are various funding agencies funding contest available, especially for the postdoctoral students. So normally there's a call, Fondesit Postdoctoral Fellowship, which is a call given by the ANID, Agency of National Investigation Desarrollo. That it is an yearly one-time call. So for that we need to have complete a PhD, and you need to write a proposal based upon your extended PhD. So you can extend your PhD, and remember it's a competitive, it's a government fellowship call. It is an independent postdoctoral fellowship. So you can apply an yearly one-time call, and especially if you are interested in working my group. So we are working on nano composite based pressure sensors, strain sensors, biomechanical energy harvesters, and also optoelectronic materials, nano composite materials for structural applications. So this funding opportunities postdoctoral you can choose. Besides that, if anybody interested in doing doctoral studies also, there is an funding opportunities from the university as well, also from the government of Chile as well. So also there are some other projects, funded projects. So those are like institution postdoctoral fellowships. So it depends upon the universities. University of Chile is a public university, so few projects are available for postdoctoral as well. Besides it, there are other private universities in Chile, so they're also encouraging institution postdoctoral fellowships as well, apart from the doctoral scholarships. So any other questions? You can
Okay, sir.
contact me through this email. I will be available to respond for your queries, and feel free to contact anytime.
Okay,
I
sir.
think
I
there
will
is a
share
question.
your mail ID in the chat box as well as in the WhatsApp groups also.
Yes,
Okay.
yes.
Okay. Thank you, sir. On behalf of our participants, I would like to sincerely thank you, our esteemed research person, for delivering an insightful session on advanced energy harvesters. Your in-depth discussion on innovative harvesting technologies such as piezoelectric, thermoelectric, and ultramagnetic energy harvester has provided us with a valuable knowledge on how to effectively capture and utilize ambient energy. The practical examples and application you shared from powering small electronic devices to supporting large energy systems were both fascinating and inspiring. This session has undoubtedly enhanced our understanding of potential and importance of advanced energy harvesting in sustainable energy solutions. So thank you once again for your time, expertise, and engaging presentation. We are look forward to more such enlightening sessions in the future. Thank you so much, sir. Uh,
Thank you very much once again. I thank the organizing committee, especially Professor Shivasubramanian sir and Dr. Ravi Kumar, for giving this opportunity,
okay,
and
sir.
happy to participate in this excellent ATAL FDP program. So I
Oh,
hope you are having an excellent feedback from the participants. There is a too many, more than like 160 participants has been joined in this excellent session. It's a uh, very good number, and it's like I hope you'll have much positive feedback from the
definitely.
other
Thank you.
professors as well.
Thank
Yeah,
you.
thank
Thank
you
you.
once
Thank you.
again.
Thank you,
Thank you so
sir,
much.
for his thought, for his this insightful and thought-provoking session on energy harvesters. We
Sir,
are especially grateful for the effort you have made to join us despite the significant time difference, as I think it's early morning in your region. Your
Mm.
dedication to sharing knowledge with us truly commendable and reflects your passion for advancing this field. On behalf of Amizar College of Engineering, I extend my heartfelt gratitude for your time and expertise. I'll thank you once again.
sir, hold a few seconds, sir. So participant, can you please switch on your video? So we'll taking few snapshots for our reference. So kindly cooperate us. Uh, uh, hold for 5 seconds, sir. I will take a snapshot.
Yeah.
Yes, sir. My job is done. So thank you, sir. Thank you so much for your valuable insights. So you can sign up the session, sir.
Yeah. Thank you. Thank you once again.
Thank you, sir. I think welcome, Dr. Balaji Garu.
Hello.
Good evening, sir.
Good evening.
Dr. Ravi, please proceed to the
Yes, sir.
presentation.
Good evening to all. It's an honor and privilege to introduce a distinguished scientist and pioneer in the field of hydrogen energy technology, Dr. Balaji sir, who currently serves as a senior scientist at the Center of Fuel Cell Technology, ARCA, Chennai. Dr. Balaji sir extensively contributes to the electrochemical research and energy technology have made a significant impact on both academic and industry. Dr. Balaji sir obtained his PhD from CSIR Karakuri in 2006, setting the stage for the remarkable career. He began as a scientist at Southern Petrochemical Industries Corporation from 2006 to 2018, working on hydrogen fuel cell. In the pursuit of advanced research, he completed his postdoctoral studies at Kitami Institute of Technology, Japan, focusing on renewable energy integrated hydrogen system. Since joining ARCA in 2010, he has been at forefront of developing innovative hydrogen energy solutions. With over years of expertise, Dr. Balaji sir research spans critical areas such as hydrogen energy technology, electrochemical process, and energy conversion systems, electrocatalyst, corrosion and electroplating, water and wastewater treatment. Among his notable achievements is the development of PEM-based electrolysis system capable of producing 5 kg of hydrogen per day, as well as establish India's first automated PM fuel cell established line. His work his work has resulted in the transfer of 5 technologies to industry, uh, furthering the practical application of his research. Dr. Balaji sir holds 5 patents, has published over 45 research papers and 4 book chapters, and delivered 75 invited talks. His contributions were recognized in 2016 with the Outstanding Scientist Award in Hydrogen Energy Technology from the Venue International Foundation. Additionally, he has mentored 39 doctoral and postgraduate students, fostering the next generation of researchers. So Dr. Balaji sir is a respected member of several prestigious committees and professional organizations, including Hydrogen Association of India, Electrochemical Society of India. Uh, so please join me in extending a warm welcome to Dr. Balaji sir, whose invaluable expertise and insights will enrich today's session. Thank you, sir. Hello, sir.
Yeah, is it audible?
Yes, sir. Yes.
Okay, okay, thank you. So, good evening, one and all. So, thanks for introductions as well as the invitations extended to be a part of this ATAL FDP. Thank you, Professor Subramanian and the other organizer. So, just I'm sharing my slides.
Okay.
Uh, is it visible my slides?
Yes, sir. Visible, sir, now.
Yeah, okay. Is it in a slideshow mode
No,
or
no.
it's
Please keep it in the slideshow, sir.
yeah, I'll do that.
Yes, sir.
Yeah, okay. So once again, good evening, one and all. The topic which I am going to discuss today is on the advanced technology for green hydrogen productions. So before getting into the topic, just I would like to give a brief introductions about brief introduction about ARCA. I think many of you aware of this ARCA because it's headquartered at Hyderabad. Actually, there are two centers are functioning at Chennai. That is Center for Future Technology, where I am coming, and the Center for Automotive Energy Materials. So these two centers are functioning at ARCA Chennai in IIT Research Park. And basically, these two centers are involved in energy related, especially hydrogen energy related, as well as lithium ion battery related activities. The main motto of ARCA is that kind of filling the gap which is existing between R&D institutions and the academia. So normally we used to work on high technological readiness level, that is high TRL level, when compared with other institutions. So the research activities which we are taking place at ARCA is we will try to scale it up to pilot scale level so that the technology validation can be done in our lab. So it would be easy for technology adoptions for the industry peoples. So that is uniqueness of ARCA research institution when compared with other national R&D institutions. And so far we have transferred about 16 technology to the 28 industries so far. And coming to our center, the Center for Fuel Cell Technology, its main activities hydrogen and based low temperature fuel cell, and also the hydrogen generation through electrolytic process. So these are the two major activities which we are currently taking up. And apart from that, as kind of spin-off activities, we do R&D on hydrogen storage as well as other battery like metal air battery as kind of spin-off technology. And apart from the technological development, we also do concentrating on human resource development because we have a PhD program in our institution, and we used to take up depending on the availability. Every year we used to take up research scholars, and we will support them for 5 years with full stipend. And they can register the PhD in any of the NITs and IITs in India. So because we have a MOE with many of the NITs and IITs in India, so they can register the PhD as a kind of external candidate. And at the end of the 5 years, will have their own PhD degree from the reputed institutions, and they can work with us actually. So that's kind of model which we are currently adapting. And apart from technology development, the manpower resource development is also a parallel pathway for our technology development. Coming to the present topic, actually, so now we are talking about net zero. So net zero solutions, the whole world is looking. So if you see the periodic table, so right now the more carbon system currently which we have. So if you want to achieve the zero, so we have to go back to hydrogen through hydrogen actually. So right now people are trying to move through the lithium batteries, electric vehicles. So that would be a kind of intermediate stage. But the ultimate stage, if you want to achieve zero, so the next you have to go to the atomic number of 1, which is having hydrogen actually. So that meet the net zero solutions of the global demand. And if you see this transition from the carbon to non-carbon based system, it won't happen in overnight actually. So we can categorize this scenario in 3 different categories, that is present, intermediate, and ultimate. So, but all those things, this energy storage mechanism, I mean, energy is through the chemistry actually, which involves chemical chemistry. And if you see this, the present scene is kind of fossil fuel based system, and maybe as a kind of intermediate stage, which we are looking as kind of electric and hybrid vehicles and biofuels actually. So through which we can also meet out the energy demand which is existing. But ultimately, the carbon-free hydrogen route will be the ultimate objective of the entire world, looking for alternative energy source for energy demand actually. So why do you want to go through the hydrogen-based energy storage mechanism is that so there are some couple of characteristics in terms of energy storage, energy density, and power density, which is good when compared with a supercapacitor and lithium battery-based energy storage device, and except the cyclic efficiency, which is lower than the battery and supercapacitor. And this part I can give you as a kind of overview on this cyclic efficiency at the end of my presentations. So so if you see all the other aspects, it is have a very good numbers in terms of life as well as the cycle life actually. And that's why people are trying to go with a hydrogen based energy storage mechanism. And if you talk about the hydrogen energy system, it's not only, it consists of multiple steps actually. That means hydrogen is not existing as such. So we need to have a very good hydrogen production method, and if you produce, it has to be stored in a proper manner because it is low, density gas, so and it occupies more volume. So we need to have a proper storage mechanism. And if you generated and stored, and the kind of transportations actually, that is also one of the key aspects when we talk about the hydrogen economy. So generation, storage, transportation, and finally the utilization with the best route of fuel cell actually. So when you talk about the hydrogen economy, these all the four steps are important. First is generation, and then storage, then transportation or distribution, and then finally to utilization. So, and even if you have all four the steps in a proper manner, so there is a kind of codes and standard and safety aspect has to be seen, unless otherwise this hydrogen full economy will not be practically viable. And the kind of skill development or education, because the hydrogen is a new energy sector, so a lot of manpower demand on this there. So we have to create a lot of awareness among the people, and kind of we have to educate the people and to handle the required skill for the hydrogen based energy devices. So when you talk about the hydrogen economy, so all these three steps are very, very important. So coming to the first steps of productions actually, because as I said, hydrogen is not existing as such, so it is it is involved, it is available in the form of hydrocarbon or water actually. So when you depends on hydrocarbon based route, again we will end up with carbon dioxide, greenhouse gases. So, but though it is emit carbon dioxide, greenhouse gases, right now the whole world is being considered maximum about more than 50 to 60% of the hydrogen is being currently produced from the natural gas actually, and through steam reformation and gasification route. And if you adopt some kind of carbon capture and storage mechanism, then it can possibly to use hydrogen with a low cost. And the next is the kind of nuclear energy. Next is the water actually. So because water is the best source for the hydrogen. So getting hydrogen from the water is also critical in terms of energy consumption. So it requires some kind of energy input. So the energy which we are getting from nuclear or renewable, so that is also most important in deciding the hydrogen production route actually. So if you see this nuclear energy, because it's high thermal energy, and using that we can directly split the water molecule into hydrogen and oxygen at a very high temperature, and we can do the same electrolysis at high temperature. So that also yield hydrogen. But ultimately, people are trying to use renewable energy because which are highly available in country like us actually. So we try to use renewable energy to split the water molecule into hydrogen and oxygen. But if you do the electrolysis process, the efficiencies is on par with the currently existing steam formation process. And depending, so these are the best route for the generation of hydrogen. But whether depending upon the feedstock and method which you are adopting for generation of hydrogen, so it can be broadly classified as brown hydrogen, gray hydrogen, blue hydrogen, and green hydrogen. So these scales are depends on the amount of carbon which we are emitting per kg per kg of hydrogen production. So if you see this, the brown, which are coal gasification method, it emit more amount of carbon dioxide, about 18 to 20 kg per kg of hydrogen. In the case of gray, that is natural gas as a feedstock and do the reformation process and get the hydrogen with the emission of carbon dioxide that is less than that coal-based system. It's about 10 to 12 kg. But if you use proper carbon capture and storage mechanism with the reformation of natural gas, it can be considered with low carbon emission of 0.6 to 3.5 kg per kg of hydrogen. But ultimately, if you get the power, that is electricity which from the solar, and do the electrolysis process and get the hydrogen and the oxygen without any carbon footprint. So that is called green hydrogen because the emission of carbon dioxide is almost zero, and that can be considered as a green hydrogen actually. Because if you do electrolysis from the grid power, that is not a green because grid power is also depends on the coal, so it is not a green. So getting the renewable energy from solar and wind and do the electrolysis, get to hydrogen and oxygen. So that is called green hydrogen with zero carbon footprint. So when you adopt the renewable energy sources and hydrogen and water as the feedstock, there are multiple ways of getting hydrogen from the water while adopting renewable energy as a source actually. So you can convert the renewable energy into heat at a low grade heat or high grade heat and directly split the water molecule into hydrogen or oxygen. That is called thermolysis because this kind of route is still existing in the R&D level. It is not mature technology because when you do thermolysis of water at high temperature, what will happen? The generated hydrogen and oxygen again will recombine to form a water at high temperature. So the recombination of hydrogen and oxygen again to form a water is a major hurdles in the thermolysis route. So and that's why this technology is existing in the kind of R&D. And the next is when you do get the renewable energy as a electricity and do electrolysis and get the hydrogen. This technology is highly mature, and that's why people are trying to adopt this electrolysis route for implementing green hydrogen in our country. But when you do this renewable energy and do biomass and do biomass gasification, and you can get hydrogen. So that is also one of the renewable energy route of getting hydrogen. But in this route is apart from the hydrogen, there may be some kind of traces of impurities which also comes along with the hydrogen. So that requires some kind of additional purification steps for hydrogen if you want to get a high pure hydrogen. And the final step is the photolysis. That means so getting the photon from the renewable, that is solar, and the photon is directly converted into electron and then hydrogen in the case of electrolysis. So getting the photon from the renewable energy and converted into electron through PV panel, and that electron is being used for electrolysis to get the hydrogen. So that is splitting of two different steps actually. Converting photon into electron, that is one step. Then next step is electron into hydrogen through electrolysis. But in the case of photolysis, it combines photon to hydrogen. So it combines two steps actually. Photon to electron, then electron to hydrogen. So that's why this efficiency of the photolysis is very, very low because it combines two steps of photon to electron, then electron to hydrogen. And that's why these steps is also is kind of R&D level. So when you see this existing technology, this electrolysis is the only route that this technology is being widely adopted and demonstrated and commercially existing. So just brief about this photolysis process. As I said, the sun has enough energy to split the water molecule into hydrogen and oxygen. But obviously, fortunately, this water does not absorb any energy from the sun. So that's why the water is existing as such water. Otherwise, it will be in the form of hydrogen or oxygen. So in order to trap the energy which is available in the renewable, so we need to have some kind of material which will first absorb the energy from the solar and then generate electrons and then it produce hydrogen. So we need to have a proper material which will do this job actually. So there are material which are available and do this kind of photon to electron to hydrogen job, but the conductivity of the material, because it has to convert photon to electron and electron to hydrogen. So the electrical conductivity of the material is one of the main challenges actually. So it required about 3 electron volt to split the water molecule into hydrogen and oxygen. But the material which are available have low energy band gap. So that means about 2.2 electron volt. Most of the useful semiconductor with this band gap in this range are photochemically unstable in water. So we require about 2.2 electron volt band gap of material which will have a sufficient electronic conductivity, and that can do this job of converting photon into electron, electron into hydrogen, but that material is not stable in the water. So there are materials which are stable in the water but does not have enough energy band gap, required energy band gap. So this is the two different challenges existing in the photolysis route. That's why this technology is still in the R&D level. And so this is the national and international status of R&D level on doing photolysis actually. And there are many people are working on the material development with a broad objective of fine-tuning the electronic band gap and the stability in the aqueous medium. And coming to the thermolysis, as I said, it is a high temperature route being carried out at 2000 degrees Celsius. So in direct temperature, it converted to hydrogen and oxygen. But at high temperature, again, this produced hydrogen and oxygen will recombine to form a water. So that's why this technology is also at a nascent level, and lot of R&D is required if you want to make a commercialized technology for this thermolysis route. So the ultimate route of electrolysis is a very good technology for making hydrogen from the water through renewable energy. So if you see this, the reaction is very simple. When you give power with a voltage of about 1.5 volts, so the water is getting split into hydrogen at the cathode and oxygen at the anode actually. But when you do this, this is the theoretical DC potential required to split the water molecule. But when you do this kind of electrolysis process, the practical case is when there are material limitation and engineering challenges. So the minimum potential required for the water electrolysis is about 2 volt actually. That is a practical voltage required for the electrolysis of water, but theoretically it is required 1.48. So there are a lot of losses is being seen while doing electrolysis process. This graph represents this kind of activation, ohmic and concentration losses. Because of that, the operating cell voltage goes beyond 2 volt actually. And if we see in terms of efficiency, that means the chemical potential required for the electrolysis is about 1.23, though it is 1.3, the thermal neutral voltage is close to 1.48, and the operating potential is close to 2, then the efficiency comes around to 65%. Then the people are trying to increase the efficiency is higher so that it can meet the PV efficiency of close to 10, because the ultimate aim to photon to hydrogen should be 10% actually. So that is the target which has been set by various Department of Energy US actually. So photon to electron and electron to hydrogen altogether it may be close to 10%. So if you see this photon, in the PV panel, the efficiency is close to 12%, and the electrolysis efficiency is 65. If you consider, then the efficiency is 7.8. So if you try to increase both the efficiency of converting photon to electron through PV and electron to hydrogen, that is through electrolysis, then there may be a possibility for increasing efficiency from overall efficiency is close to 10%. So as I said, this electrolysis is like an electrochemical process. So basically, you need to have a positive or negative electrode, and pure water does not conduct electricity. So we need to have ions in the water so that it can conducting. So depending upon the type of ion which you are using for the electrolysis, it can be categorized as alkaline, acidic, and oxide ion. So if you see this alkaline, the potassium hydroxide and sodium hydroxide salt is being added with pure water, so that water will be electrically conductive, ionically conductive, sorry. So, and using positive and negative electrode, you can do electrolysis. Whereas instead of alkaline, if you use acidic like sulfuric acid, then you can make a water as a conducting medium. And if you see this polymer electrolyte membrane, which is nothing but in layman language, is a kind of solid sulfuric acid, because ionic conduction will take place in the membrane form. So that is called polymer electrolyte membrane based water electrolyzer. And the anodic and cathode reactions are oxygen evolution and hydrogen evolution respectively. And the operating temperatures are room temperature, in the almost slightly above the room temperature. and less than 100 to 150 degrees Celsius. Whereas in the case of solid oxide based electrolysis process, this conduction ion is oxide ion. So if you want to make oxide ion conduction, then this oxide ion conduction will be effective only at a high temperature. So you have to do this electrolysis process at high temperature of close to 1000 degrees Celsius. Then only you can make the process viable. But these solid oxide based water electrolysis processes are only at R&D level because of the material limitations. Because the material stability at very high temperature, at the same time it should have a reasonable electronic conductivity, and these two aspects are bottleneck for commercializing this technology for the hydrogen production. So, as I said, this alkaline is a mature technology which is widely adopted internationally in commercial scale, and these polymer membrane based electrolysis processes are also nearing commercial stage, except the cost is one factor which is hindering the easy adoption and wide adoption of PEM based technology for the hydrogen production. As I said, the solid oxide is only at the research level actually. And if you see there's a material requirement to perform this electrolysis process in water, there are 12 non-precious metal and 2 precious metals are eligible for the hydrogen evolution in the water electrolysis process. So if you see this, periodic table, so only 12 non-precious metal and 2 precious metals are available for making this hydrogen evolution from the water. Because why these elements are alone favoring the hydrogen evolution is that because when you do the splitting of water molecules, the hydrogen at proton which is liberated at the cathode, first it has to bind with the metal and then it has to come out from the metal actually. So this is a two-step process. So the binding energy with the metal has to be optimum. It should not be highly binded. At the same time, if it is binding energy is too more, then this desorption process also takes much energy. So it should be kind of optimum of binding energy with the metal and the hydrogen. So based on this concept, these 12 non-precious metal and 2 precious metals are preferring for the hydrogen evolution in the water electrolysis process. And coming to the oxygen evolution side, actually, so that is also one of the slow process. So most of the energy which is being utilized only for the oxygen evolution, not for the hydrogen evolution actually. So when you do electrolysis process, most of the energy is required to evolve the oxygen evolution than the hydrogen evolution. Because when you do oxygen evolution, actually, so because it has to combine the oxygen, nascent oxygen, this one oxygen atom has to be combined with another oxygen atom to evolve as a O2 molecule. So the oxygens are two oxygen atoms are electrochemically negative. So electronegative is more. So combining these two electronegative atoms and to evolve as oxygen is a high rate determining step and slow step. So we have to choose proper material for performing this oxygen evolution reaction. Basically, we can adopt any metal oxide, especially noble metal oxide, ruthenium oxide, and iridium oxide, which is the best material for the oxygen evolution. Because when performing this oxygen evolution, what will happen? The metal first it will get oxidized in its oxide form. So instead of that, if you use oxide, which is have a very good electronic conductivity like metal, then we can minimize the losses which are being encountered during this oxygen evolution process. That's why the iridium oxide and ruthenium oxide is the best electrocatalyst material for the oxygen evolution reaction, which will directly favor the oxygen evolution instead of metal oxidation. And so coming to the alkaline based system, because when you do this alkaline based water electrolysis process, the advantage is that we can use cheap electrode material, that is nickel based electrode material can be used, and it does not require any special material for the construction of the cell. So that is the advantage. And disadvantage in terms of operational efficiency, because the hydrogen production rate depends on amount of current which you are pumping for the electrolysis process. So if you pump more DC current to the electrolysis process, the more amount of hydrogen will be there. So, but if you use this concept in this electrolysis process, the nickel will not favor the operation of electrolysis process at high operating current. So if you pump more current to the electrolysis process, then nickel will start decorrosion. Actually, nickel will lose its stability, and instead of favoring hydrogen oxygen evolution, it favors the metal dissolutions and metal instability. So that's why this alkaline water electrolysis process is being operated at low operating current density, and that makes system very large in size and uh, low efficiency. So, but we can use a non-noble metal based catalyst, that is preferably nickel based system. And if you can use a diaphragm based separator because you are producing hydrogen oxygen in two different compartments. So obviously you should avoid the mixing of hydrogen and oxygen in the same compartment. So you must have a gas separators which can be as a kind of asbestos space. Nowadays it is being replaced by zirconium oxide based material, and which is act as a gas separator which will completely separate the produce hydrogen and oxygen gases. And that is the traditional technology for making alkaline water electrolysis for hydrogen production. So now the people are widely working on enhance the efficiency of alkaline based system, because though nickel is being used in any electrochemical system, if you try to reduce the inter-electrode distance, positive and negative electrode distance as close as possible, then you can make this electrolysis process efficient. So that's kind of zero gap and narrow gap configuration of cell design which are being adopted for making alkaline water electrolysis process much efficient. And nano electrocatalyst, because instead of using micron size nickel electrocatalyst, if you go with nano materials like nickel and alloying of nickel with cobalt and iron, that also makes sense and make system more efficient than the traditional nickel based alkaline water electrolysis process. And the status on alkaline water electrolysis system in our country, BARC is one of the leading organization, and they developed a 10 kilowatt system and 30 meter cube system, and they transfer the technology to the 9 industry in this country. And CSIR Sikri also developed a various electrode material which can reduce the energy consumption for the hydrogen production. And Energy Research and Development Association, it's a Gujarat-based PSU, has also demonstrated the PV power coupled alkaline water electrolysis for the hydrogen production. And National Institute of Solar Energy, Gurgaon, that is, it comes under Ministry of New and Renewable Energy R&D institution. So they have demonstrated the PV coupled alkaline water electrolysis for the hydrogen generation. This hydrogen generated through this electrolysis process is being stored and utilizing for as a kind of gas dispersing system. So these are the major program and on alkaline electrolyzer in this country. And this is the photograph of the National Institute of Solar Energy, which they have demonstrated the PV powered alkaline water electrolysis system, and we can find this this gas dispensing station which are at Gurgaon actually. And coming to next electrolysis process of solid oxide water electrolysis, as I said, if you want to carry out the oxide ion conduction in the electrolyte, you need to heat the cell up close to 1000 degrees Celsius, and you must use a ceramic based material for cathode and anode. When you use ceramic based material, obviously the electronic conductivity will be less, and it will be high only at high temperature. So nickel stabilized, yttrium stabilized, zirconium composite material is preferred material for the cathode and anode. And the electrolyte is basically ionic mobility introduced by zero valent doping of yttrium stabilized zirconia. So yttrium stabilized zirconia is the major material which is being used for the construction of the electrode material as well as the separator as well as the electrolyte actually. So because of the material degradation at high temperature, this technology is not yet being commercially matured. So it is still in the R&D stage actually. So coming to the next method of producing hydrogen through a water, that is polymer electrolyte membrane based system. Basically it's acidic electrolysis process. So here we are not using any aqueous based acid. Instead of using this liquid based acid, we use the membrane, which is having very good ionic conduction, especially protonic conduction, and that will act as an electrolyte. It's a kind of polymer sheet, and on both sides of the polymer sheet, the catalyst material is being coated. So one side will act as anode, another side will act as a cathode. And this is the typical configuration of the single polymer electrolyte membrane-based water electrolysis process. So you have a membrane, and both sides of the membrane you are coated with a catalyst, and you have a proper because you have to pump the water within this membrane electrode assembly. So you must have some kind of flow channel that is called flow field plate, which is having one inlet, one outlet, which will facilitate the water transport inside the membrane. So, and this is the typical component for water electrolysis PEM-based system. And the advantage when compared with alkaline is that you can pump more current. As I said, you can operate the system at a very high current density so that you can produce more amount of hydrogen with a less space actually. So the stack, you can arrange the multiple cells in a parallel and series mode. So you can make system very compact and highly efficient, and you can produce more amount of hydrogen in a smaller system. So that is the advantage. The major disadvantage is that we have to use only noble metal based catalyst, that is platinum, iridium, ruthenium based electrocatalyst material has to be used for the electrode material fabrication, and the membrane is also one of the very costliest component actually. So that makes the system expensive. Rest of things, the operational point of view, it is very, very safe, and you can handle very pure water instead of alkaline water. So you can pump only demineralized high pure water to the system, and we can get the hydrogen and oxygen in a different compartment. And second advantage is that the membrane is not only act as an electrolyte, it also acts as a separator. Because you are producing hydrogen and oxygen in two different compartments, you have to separate the gas molecules actually. So the role of membrane is not only as an electrolyte, it's also a separator. So that is one of the advantage of going with the PEM-based system for the water electrolysis process. As I said, here the platinum is widely used as the cathode material, and as I said, when you are going with this noble metal catalyst, obviously people will try to reduce noble metal content in the electrode actually. So how we can reduce the noble metal content in the electrode is that, so you can incorporate any carbon-based conducting material along with the catalyst material, so that the noble metal loading will be less. So in that aspect, actually this noble metal, the carbon can be used as a supporting material, but this carbon-based support material can be used only at the cathode side, not at the anode side actually. Because when you do the electrolysis process, obviously the cell potential is close to 2 volt. At that 2 volt, if you see this, the hydrogen evolution side is only close to 0, maybe 0.1 or 0.2 with considering over potential. So most of the voltage loss is occurring at anode side. That the anode potential is close to 1.5, 1.6 actually. So altogether the cell potential will be close to 2. But the anode side, the potential is higher than the cathode side. Obviously, the carbon-based material will not be stable because the carbon undergo corrosion at this acidic environment under that particular potential. So you cannot use any carbon-based material at the anode side. But whereas in the cathode side, the cell voltage is very less, and so the carbon corrosion start at 0.9 volt. So in the case of cathode side, the voltage will be less than 0.9, is close to 0.1 and 0.2. So you can use any carbon-based support material for the noble metal catalyst actually. Whereas in the case of anode side, actually, you cannot use a carbon. So you have to use some silicon carbide or titanium oxide. The metal oxide is a very good catalyst support, which is having reasonable electronic conductivity and also reduces the noble metal content of the anode electrolyte catalyst. So the next important component is the membrane. As I said, it is act as an electrolyte as well as separator. And this the uniqueness of this membrane is basically a Teflon, which is polytetrafluoroethylene based polymer compound, which is being functionalized with sulfonic acid group. That is called SO3H group. This SO3H group is responsible for the proton conduction. So this the proton conduction will be effective only the membrane is fully hydrated actually. So when you make membrane highly hydrated, then only the proton transport from the cathode to anode will happen very quickly. The ionic conduction rate is high, so you can perform this electrolysis process at very high current density. So and as I said, this electrochemical process, when you do the electrolysis process at room temperature and at high temperature, obviously the electrical energy input will be lower when you do this electrolysis part at a high temperature. So that's why the people are trying to use this electrolysis process little bit elevated temperature, more than 100 degrees Celsius. So when you do electrolysis process more than 100 degrees Celsius, this Nafian based, that is PEM based system may not withstand, because the proton conduction in the Nafian will be effective only at less than 100 degrees Celsius. But if you want to perform the electrolysis process more than 100 degrees Celsius, then obviously you have to see some kind of high temperature membrane, which will take care of the proton conduction even at high temperature. So in that concept, actually people are doping some metal oxide and imidazolium based, because this is sulfonic acid based membrane for the Nafion. But there are membrane which can handle the proton conduction without water. So in that concept, this imidazolium based membrane, which can operate at high temperature, when you do the electrolysis, PEM based electrolysis at high temperature, obviously the electrical energy input for the electrolysis process will be less, because you are supplying some form of energy in the form of thermal apart from the electrical. So when you consider that, obviously the energy cost, thermal energy is cheaper than the electrical energy. That's why people are trying to operate the system at high temperature to reduce the electrical energy input for the hydrogen generation. And another important component, as I said, you have to facilitate the water transport within the system. So you must have a proper flow channel. So in order to make a flow channel, so the titanium based material, which is having desired flow channels, maybe serpentine, parallel. So there are multiple flow configurations are available to increase the velocity and reduce the pressure drop while you are operating the system. And this is titanium. So when you, even if you use a titanium based material, so that also undergoes some kind of oxidation process. We want to avoid the oxidation process, so it has to be coated with the platinum. So platinized titanium, which is being widely used as a flow field plate for PEM-based water electrolysis process. So once if you make a stack, that is a number of combination of more cells, and you assemble as a kind of stack. Apart from the stack, you need to have a other balance of system, that is called water supply system, power supply, DC power supply system, and hydrogen which is coming out from the electrolysis process highly humidified. So you have to drain the hydrogen gas and you have to compress the hydrogen gas for storage. So it includes, apart from the stack, other balance of system like power supply system, reactant supply system, and gas processing steps, that is dryer and compressor, which all includes as a kind of PMFC system for the hydrogen generation. And this is the some of the development which happened in our country. So I mean, ARCA also working on this PEM based electrolysis process, but not water, but it's also PEM based system. And the SPIC Energy Research Group also has demonstrated 0.5 to 1 meter cube of PEM based system, and CSIR, SICRI, and JNTU also has demonstrated the prototype for the development of PEM based system. Right now, many people are involved in making various kind of materials as well as system after the announcement of National Hydrogen Mission, actually. So if you see the global scenario, especially in the PEM-based alkaline-based system, only 33 medium to large scale manufacturers are available in the whole world, actually. So the whole world is completely rely on these 33 manufacturers which are existing in the global market. Among in these 33, about 20 manufacturers are concentrating on alkaline-based system. Only 12 manufacturers are concentrating on PEM-based system. And these are the existing lead manufacturer, both in the case of alkaline and PEM. And SOEC, there are few people are developing system based on alkaline, I mean, based on solid oxide electrolysis process, but that yet to be matured, actually. So, and their development and their key energy consumption for the hydrogen production. But the thumb rule is if you want to produce 1 kg of hydrogen, so you must spend about 55 to 60 kilowatt hour of energy, electrical energy has to be spent. So about say for example, though the theoretical energy consumption is close to 35 unit of electricity, but the practical case, including other BOP component power consumption, if you want to produce 1 kg of hydrogen from the water, practically you have to spend about 55 to 60 unit of electricity. So right now, if you see the electricity cost of 1 unit of 5 rupees or 7 rupees, so and multiply with 60, it comes to close to 500 rupees actually. So that is the cost of the present hydrogen which is produced from the water electrolysis process actually. And now the people are trying to reduce the energy consumption for the hydrogen production because the theoretical energy consumption is close to 35. So people are trying to reduce the energy consumption in terms of novel material development and novel design of electrolyzer and effective operation, and all those is attempt will make the energy consumption lesser than the currently existing energy consumption. And and coming to the cost aspects of this electrolysis process, so about 40% of the cost goes to the stack development, which is the key, and 60% and another 40% close to the power supply, because the power supply is a kind of DC power supply. So if you use renewable energy source, then the power component, power electronic components is also playing a major role. And because the electrolysis process requires steady DC current, but the renewable energies are too fluctuating, so you may need to have a proper power conditioner and power supply. So that makes the system cost much more higher. So about 40% of the cost also goes to the power supply apart from the stack actually. So this is a kind of cost component analysis for the various components if you want to make a electrolysis system. And coming to the because of the advantage of going with the green hydrogen route, so the our Indian government is announced a national green hydrogen mission in 2023. So the main aim of national hydrogen mission is that the hydrogen is not new for the chemical industries, which are widely used actually. If you take steel industries and refineries and fertilizer, which are already they are using hydrogen actually. So if you take refinery industries, they are using hydrogen for the desulfurization process. And if you take fertilizer, so they are making hydrogen from the naphtha and making ammonia. So the ammonia synthesis required hydrogen. So the hydrogen coming from naphtha. And if you take steel industries, if you want to convert iron ore into iron, so it is a reduction process that's also required hydrogen actually. Right now it is being carried out with the carbon as a reducing agent, and the emission of CO2 is more. So that's why the steel, fertilizer and the refinery industries has to be adapted green hydrogen because they are in need of hydrogen. That requirement is being currently fulfilled by the gray hydrogen or blue hydrogen, which are coming from the carbon based material store. So now the government is pushing them to go with a green hydrogen electrolysis route so that they can reduce the carbon footprint which is being emitted by these three kind of industries. So that is the major mission of the national green hydrogen. And subsequently, after announcement of the national green hydrogen missions, so these are the various projects being undertaken by the Indian government at various in the major sector of refinery, steel, and the fertilizer industries, and the existing status of the project actually, which is being highlighted in this table. And if you see this, ultimately, if you want to reduce the hydrogen cost, you have to reduce the electrical energy input and you have to reduce the cost of the system. So capex and operating capital expenditure and operating expenditure both has to be reduced. Then only this cost of the hydrogen which is being produced from the water resources can be reduced considerably. So there's a kind of trade-off actually. Because when you reduce the capex, so obviously you have to end up with a higher operating expenditure. So when you reduce the operating expenditure, you have to end up with a high capital expenditure, capex. So it's a kind of trade-off, and without losing the efficiency and the durability, because when you invest crores and crores of money for establishing this electrolysis process, so we have to consider the life of the system, life of the plant actually. So all these, the capex and operating expenditure and the efficiency and the durability. So these are the four pillars. So it's a kind of trade-off, because if you focus more on the efficiency, then you will end up with a high capex and opex actually. And if you focus on more on durability, then again you will end up with the capex and opex. So it's a kind of proper combination is required to achieve the low cost hydrogen from the electrolysis process. And right now, this electrolysis process is being adopted in chloralkali industries actually. So the chloralkali industries, what they are doing, they are not doing any water electrolysis process. Instead of water electrolysis process, they are doing brain electrolysis process. Basically, the water, sodium chloride is mixed with sodium chloride and do electrolysis process. So they will get a three useful product. Only is hydrogen at the cathode and chlorine at the anode, and the sodium hydroxide is also one of the good product actually. So right now the sodium hydroxide is widely used for many industry applications, and the chlorine is not widely used actually, because the chlorine is a kind of environmental impact, but not that. That's why the chlorine does not have any commercial value. But the hydrogen which is being produced by the chloralkali industries as a byproduct is currently we are using as a hydrogen cylinders. So in India, if you try to get the hydrogen cylinders, high pure hydrogen cylinders, so that hydrogen is being coming from these chloralkali industries, which are being produced as a byproduct. So when you want to realize this kind of hydrogen mission very quickly, this chloralkali industry product, I think sodium hydroxide, chlorine, and hydrogen. So if you make sodium hydroxide and chlorine is also a viable product for the consumption, then obviously the hydrogen cost will also come down. So whereas in the case of water electricity, you will produce hydrogen and oxygen. Oxygen is not being widely used actually. So if you produce hydrogen along with sodium hydroxide and chlorine and make all the three components are commercially viable and commercially utilizable, then the hydrogen cost is indirectly will come down. So that is one of the aspects which need to be considered if you want to reduce the hydrogen production cost actually. So that is a overall scenario of the electrolysis process. And coming to major activities which are taking place in our research center is that electrolysis is high TRL level, and we do electrolysis process for hydrogen production. And we also concentrating on hydrogen from metal hydrate, that is chemical route. So that is a little bit low TRL level. And as I said, we are also working on developing materials for the photoelectrochemical route, that is called photolysis route. And the electrolysis which we carried out is not conventional water electrolysis, because as I said, you have to give about 55 units of electricity to produce 1 kg of hydrogen from the water. But if you get the hydrogen and store it in the form of cylinder, again, if you want to get the power from the hydrogen, that is called fuel cell actually. So the electrolysis and fuel cell is reverse reaction. So electrolysis is nothing but giving power, electrical power, and splitting water molecule and producing hydrogen and oxygen. That is electrolysis route. In fuel cell, what it is exactly reversed. When you use hydrogen and oxygen in the system, you will get a power and water. So it's exactly reverse of the water electrolysis process. So when you see these reactions are common, H2O will give hydrogen, H2O plus power will give hydrogen and oxygen, and hydrogen and oxygen, the reverse reaction, the hydrogen and oxygen will give water and power. So if the reactions are same, then energy input and energy output should also be same. That is what the theory says. But as I said, though the theoretical energy requirement for production of hydrogen is about 35 units, practically we are spending about 55 to 60 units of electricity to produce 1 kg of hydrogen. So if you use this 1 kg of hydrogen in fuel cell, we have to get again 55 to 60 units of electricity. But normally we won't get it. So we will get only 15 units of electricity. So the energy input is about 60 and output is 15. So the efficiency is close to 25%. So that's why we try to minimize the energy input required for the hydrogen. In doing electrolysis process, the major loss is occurring at the anode side. So that is what oxygen evolution side. So we try to compromise the oxygen evolution side. So when you add some kind of alcohols like methanol and ethanol, so it's a low molecular weight alcohol and low carbon content, and we can produce hydrogen the same electrolysis process, and hydrogen and carbon dioxide. So this carbon dioxide is emission is less, but when you have a proper carbon dioxide capture, the hydrogen which we produce is very low energy consumption. That means 1/3 of the water electrolysis process. So because in this methanol water electrolysis process, you can get the hydrogen, it's about 15 unit of electricity for 1 kg of hydrogen. So the energy input is 15 unit, and if you use the 1 kg of hydrogen in the fuel cell, you will also get a 15 unit of electricity. So now the energy is almost balancing. Electrical energy input and output is almost balancing. So with that concept, we developed this technology of developing PEM-based electrochemical methanol reformer for the hydrogen production, which produce more than less electrical energy input than the water electrolysis. And another advantage is the input voltage is less than 1 volt, 0.5 to 0.6 volt per cell. So obviously you can use any carbon-based material, because when you do electrolysis process more than 1 volt, then obviously carbon-based material cannot be used because it undergo corrosions. So in this case of methanol water electrolysis, you can operate electrolysis process less than 1 volt. So we can use any carbon-based material for the cell construction. And second advantage is that this methanol water mixture can be converted into hydrogen and carbon dioxide in chemical route also. But when you do this chemical reformation process, the hydrogen is coming along with carbon dioxide. So you have to have a separate purification systems actually. Whereas in the case of PEM-based system, you don't want to do purify the hydrogen because you have the membrane. So that will take care of the separation of hydrogen and carbon dioxide, which are producing in the respective compartments. So the hydrogen which is coming out from the system is completely pure. You don't want to adopt any purification system further. So that is also one of the advantage. And operation temperature is also near to ambient conditions. In the case of chemical reformer, we have to operate at high temperature of 250 to 300 degrees Celsius. So when compared with the electrolysis, when compared with the chemical reformer route, this electrochemical reformer route is much more viable for the practical adoption. So with that concept, this is our journey. We developed from the smaller scale to 5 kg per day of hydrogen production. This is the pilot plant which we have in our laboratory, and which can produce about 5 kg of hydrogen with the emission of carbon dioxide. But now we try to adopt carbon capture method also, so that the gray hydrogen will become blue hydrogen with a low energy consumption. And this is the photograph of the developed system in our laboratory. It is produced about 5 kg of hydrogen through electrolysis of methanol water mixture. And if you see this state of the art performance of the electrolyzer and what we need if you want to reduce the capex of a hydrogen generator as well as operating expenditure of the hydrogen. So most of the thrust area is the kind of membrane development actually, because the membrane as separator is a crucial component in developing this electrolysis electrolysis process. So most of the R&D is required on the membrane as well as the best electrocatalyst material, which will take care of the cost of the system as well as operating cost of the system. And so as I said, if you want to reduce the cost, there are multiple approaches. It is called a depolarizer because we are compromising the oxygen evolution at the anode side. So if you adapt methanol along with water and ethanol along with water, or some kind of urea, aqueous urea electrolysis, aqueous methanol, aqueous ethanol, and even carbon, we can combine with water and we can produce carbon dioxide and hydrogen, and which is also required low energy input for the hydrogen generation. So this kind of approach is being called as depolarizer because it's polarize the oxygen molecule. So and end up with a carbon and oxygen kind of carbon monoxide. Our strong belief is that more carbon to no carbon transition will not happen overnight. So we have to adopt more carbon, less carbon, then no carbon. So that is the stepway mechanism which we need to adopt. So low carbon system is a intermediate pathway for hydrogen generations with much cheaper cost, and ultimately we can go with the water-based system. And there are because this is a kind of decoupled water electrolysis, because in some electrolysis process, the hydrogen is oxygen is being produced simultaneously. That is the conventional electrolysis process. First, the decoupled in the sense is that the hydrogen oxygen evolution will not happen simultaneously. First, the hydrogen evolution will happen. Whatever the electron which are liberated by the cathode being absorbed by some redox mediator, then it will favor the oxygen evolution later. So it's a kind of a delayed oxygen evolution mechanism, hydrogen evolution mechanism, that is called decoupled water electrolysis. Is a kind of advanced electrolysis process for the green hydrogen production. And there is a concept of membraneless electrolysis process, because as I said, most of the cost is going for the development of membrane and separator for the gas evolution. But there is a concept going on membraneless, because when you do electrolysis process, the hydrogen and the oxygen are being produced the respective electrode, but it takes some time to combine again to hydrogen oxygen mixing. So if you want to avoid this hydrogen oxygen mixing, you can use membrane. So in this concept, if membrane is not there, so you have to reduce the retention time of the hydrogen which is being produced at the respective compartment of hydrogen as well as oxygen. So if we reduce the retention time of hydrogen oxygen in this compartment, so you can favor the hydrogen oxygen evolution without any separator or membrane. So that is the concept. So a lot of flow dynamics is required, and it's an upcoming concept of membraneless water electrolysis process. So a long way we need to go if you want to make this technology commercially viable. And if you see, ultimately, if you produce hydrogen in any method, so ultimately the cost will determine the hydrogen, whether it can be cheaper for the adoption. So right now, the natural gas that is called steam methane reforming method is a cheaper one, that is about $2.5 to $3 per kg. When you adopt the nuclear energy for the electrolysis, thermal electrolysis process, it considerably reduced to $1.84 per kg. But the case of water electrolysis, because of the high energy input, right now, this about close to $5 to $7 per kg. The technology which we use, methanol-based electrolysis process, it's realizing closer to the methane reforming process, about $3 to $3.5 per kg. So we need to consider the hydrogen production cost, what method you can adopt, but ultimately the cost of the hydrogen has to be less actually. It's a kind of comparison, because here the hydrogen I'm saying as a kind of energy storage medium, because you have a renewable energy power. Right now the battery is the storage medium. So when you do battery storage as a renewable energy storage medium, and whenever you require, you can discharge the battery and get the power. So the same kind of methodology if you adopt, getting the power from the renewable and splitting the water molecule into hydrogen and oxygen. So it's a kind of charging process, and store it in the respective cylinders actually. Whenever you require, give this hydrogen and oxygen in the fuel cell, again you get back the power and water. It's a kind of discharging mechanism of battery. So that's why the battery and hydrogen both are being considered as a energy storage medium. So if you say both are energy storage medium, ultimately which one is better? The questions obviously will come. So in that aspect, if you see that I have considered here is a lithium battery and hydrogen fuel cell. It's called regenerative hydrogen fuel cell. That's why I named as RHFC and lithium battery. So there is a term energy stored on invested actually, which is nothing but you have to spend some amount of energy to make 1 kilowatt battery. So that is being energy required to manufacture such a device actually. And from that device, how much of energy you are getting throughout the lifetime actually. So this ratio is nothing but energy stored on invested. So if you consider this term for the lithium battery, it is low, because the amount of energy which you want to spend to make 1 kilowatt battery, which is higher than 1 kilowatt electrolyzer or fuel cell actually. So that's why the energy stored on investment is low for lithium battery, whereas in the fuel cell or electrolyzer is high. But the net efficiency, because if you store 1 kilowatt power in battery and you can get about 0.8 to 0.9 kilowatt power from the battery, the efficiency is 80% or 90%. Whereas in the case of electrolysis, as I said, theoretically it's required 35 unit of electricity, but practically we are giving 60 unit of electricity for 1 kg of hydrogen. With that 1 kg of hydrogen in fuel cell, if you use only 15 to 20 unit of electricity, you get back. There is a kind of losses actually. So these losses are being created by the material and design, because the reactions are common. Hydrogen and oxygen will give water and power, and water and power will give hydrogen and oxygen. Obviously, the energy input and energy output should be same in theoretically. The theoretical voltage for the electrolysis is 1.5 and practically we are giving 2 volt. So there is a scope for a reduction of voltage close to 1.5 with innovative material design and material aspect. The same thing in the fuel cell, we will not get when you give hydrogen oxygen in the fuel cell, you must get 1.5 volt as open circuit voltage. But you won't get 1.5 volt as open circuit voltage. Instead of that, you will get only 1 volt actually. So there is a loss of 0.5 volt in the open circuit voltage. So, but that's also, there is a kind of material limitation and design aspects. So there is a lot of scope to reduce this potential window close to input and output. So if you make novel material and novel design, so there is a lot of scope for the efficiency of round trip efficiency close to 50%. So, but we cannot, so close to 50%. So the round trip efficiency is close to 50%, and energy stored on investment is also better than the lithium ion battery. Then this hydrogen based energy storage mechanism will be the ultimate for the energy storage mechanism. So that's what this slide shows actually. This is kind of analysis has been carried out by some researchers actually. So this hydrogen based economy will be the ultimate energy storage, but there are some challenges which has been listed out here actually. That is one of the production costs. Even if you produce the kind of storage mechanism we need to have, because whether it's a gaseous form storage or it's a liquid form or a solid form, so we have to have a storage mechanism and supply chain. So how we are going to transport the hydrogen gas to the respective need actually. So these are the 3 major challenges which yet to be addressed. Apart from that, there is a kind of debate is going on. Where is the source for water? Already we have a water scarcity. So when you do adopt a green hydrogen, where is the source for water? The answer is not that critical actually. The water is not a big issue in terms of green hydrogen generation, because right now the desalination plant are well established. So we can do the desalination from the seawater and get the pure hydrogen, pure water, and which can be adapted for the green hydrogen process. But later, the fuel cell technology will, if it is developed on parallel with the electrolysis process, whatever the water input which we generated, which we given for the hydrogen generation, you can get back the same amount of water when you do the power generation through fuel cell. So water scarcity and water-based challenges will not be a major hurdle for the green hydrogen adoptions. And there are, so because of that, there are plenty of opportunities in terms of research area, in terms of commercial and validation aspects. So a lot of scopes are there, so which can be considered for the as a kind of opportunity instead of challenges actually. And worldwide, the National Hydrogen Fuel Cell Day is being celebrated. So the 10th October, because it's the present atomic weight of hydrogen, 1.008. So 8th October every year is being internationally is celebrated as a National Hydrogen Day to make awareness among the people how the hydrogen is important, hydrogen energy storage mechanism is important for the energy demand. So we also celebrating National Hydrogen Fuels Day for the past 7 years. And in terms of conducting various events and workshops and conference and demonstration program. And as I said, I would like to conclude. Now we are dealing with more carbon system, that is less hydrogen actually. But the carbon cannot be completely eliminated, but it can be minimized with more hydrogen. So more hydrogen, less carbon footprint. We can play with we can consider the hydrogen as a best energy storage medium. So with that, I conclude my talk and I'm open for any discussion. Thank you for your attention.
Thank you, sir. Dear participants, I think if you have any kind of queries, please type in the chat box or you may raise your hand.
Dear participants, kindly, if you have any queries, please text in the chat box, or else you can speak to Balaji sir directly. Yes, sir.
Nagaraj.
Nagaraj sir, you just please continue.
Hello, sir.
Yeah, please.
Sir, in membrane studies, people are also adopting CFD technologies now. So, is there any useful guidelines regarding that, implementing CFD to study this membrane related?
Actually, the CFD is mainly used for the flow dynamics actually. So because in the case of PIM-based system, the flow dynamics is very critical, which will contribute the energy in terms of energy consumption because most of the losses are being carried out, I mean, being considered due to the improper flow and distribution among the electrocatalyst surface. So
Sir.
the CFD analysis is also playing a major role in arriving a proper flow channel, the flow design, and the flow field plate actually. So which is also most important. There is a kind of theoretical studies is also required to fine tune the proper flow channel actually for the water as well as the reactants.
Okay, sir. Okay. So, typically, the CFD study is parametric study helpful to design any hydrogen reactor. I mean,
I didn't get you, sir.
like this parametric study need to conduct to finalize the design or membrane side.
No, only the design, not on the membrane side actually.
Okay.
So only on the design actually, especially the flow field design actually, which will take care of the transport losses actually. So the membrane is a different polymer chemistry actually, polymer technology. So that studies is different from the CFD actually. The CFD is mainly used for to ascertain the flow channel distribution and flow velocity and the kind of pressure distribution loss. So these kind of aspects can be considered the CFD is the best tool.
Okay, sir. Okay. Thank you.
There is a query in Krishna Varma sir.
Yeah.
In the chat box.
Can you read out the
What are the hindrances for the hydrogen buses in India, sir?
Actually, it's basically the cost one. If you eliminate the cost aspect, the second aspect is storage actually. Because if you do 1 kg of produce 1 kg of hydrogen, and if you want to store it in the onboard vehicle, because it's a lighter gas, it occupies more volume. So you have to compress the hydrogen at an elevated pressure of 700 bar actually. So the commercial hydrogen cylinder which are existing in the market is 150 bar because when you compress hydrogen more than 150 bar in the steel cylinder, the hydrogen has the nature of hydrogen embrittlement because it penetrates the metal matrix of the cylinder and create the kind of internal stress in the metal matrix and it leads to explosion. So you cannot use any steel-based cylinders for the hydrogen at elevated pressure. So you need to have a proper carbon composite cylinders. In that kind of cylinder material, carbon composite cylinder material, which can handle hydrogen at 700 bar. So you have to have a 700 bar hydrogen storage cylinder material and the construction, and you need to adapt 700 bar storage pressure of cylinders in the vehicle. Then only you can extend the range actually. So then only you can extend the, say for example, passenger car or bus. So you must carry 5 to 6 kg of hydrogen in the onboard. So, if you want to carry such kind of huge volume of hydrogen, so you have to just be compressed at a high pressure. So, and in Indian government right now, they have not give license for handling hydrogen cylinders more than 200 bar. So, because of the safety aspects, but internationally it has been handled up to 700 bar, and the passenger has been demonstrated. The Toyota Mirai is one of the live fuel cell car, which you may be aware. So soon this technology will also be adopted, and once if you are familiar with operating hydrogen gas with elevated pressure, so the slowly the 700 bar pressure cylinders can also be handled. So once if it comes, then the fuel cell buses or hydrogen based buses will be on road actually.
There is a query in the chat box, sir.
Yeah.
Where India is standing in the production of H2 as a beginner, where we can start the production of H2 and its uses. What facilities we can do required to start the research?
Yeah, that's a good question actually. The right now the India the required hydrogen is being met out by the reforming of hydrogen through methane. So methane reformer is the existing technology which produce hydrogen and is being used for the refinery, steel and fertilizer industries. So, but there is gray hydrogen which will also emit carbon dioxide along with hydrogen. So we have to do the water-based system for the generation of hydrogen. So as I said, the water-based system, if you use the pure water is the need of the hour actually. So, and we don't want to depend only on pure water. So you can do some kind of alternative wastewater and other impure water. When you do impure water electrolysis and wastewater electrolysis is also a different perspective of electrolysis process, and that also emit hydrogen and not carbon, oxygen, maybe some other useful product. When you do wastewater treatment electrochemically, you will also generate hydrogen, but the water will also get treated actually. So in that aspects will be the good actually for the research community. You can look up the local wastewater, regional based wastewater, because the wastewater will have a different composition and different need, different industries. So you can particularly focus on nearby industries where the wastewater is being used, and you can collect and you can find out the cheaper electrode material. We don't want to go with the good noble metal like platinum, iridium, ruthenium. So you can have a small electrochemical workstation is required initially when you want to use the kind of studies, which does not cost about more than 2 to 3 lakhs actually. So with that, you can start our R&D program using some wastewater analysis, and there are plenty of literatures also available. So you can start with that.
I have one query, sir. Actually, I have developed one project proposal for one funding agency.
Yeah. Okay.
So that concept is like methanol steam reforming using for solar parabolic trough collector, sir.
Okay.
So
It's a
there
chemical
is
reformer you are meaning?
yes, sir. For a heating source, I used solar parabolic trough collector as a heating source, sir.
Okay.
But they're actually from literature studies, I just gone through that copper, zinc oxide, and aluminum oxide actually they are used as a catalyst material.
Yeah.
So is there any other catalyst material which will be used a better option for choosing that catalyst material?
I think the copper zinc oxide base is the proven electrocatalyst material for the chemical reformer actually.
Okay, sir.
So because your major objective is kind of using solar thermal heat actually. So you don't want to don't want to concentrate on the catalyst aspect actually. You can play with the existing commercial catalyst based system, and that is well proven actually. So there are a lot of R&D to reduce the copper content and all those things are, but right now the copper zinc oxide based material is the proven technology for this chemical reformer.
And main challenge I was facing was that the solar radiation was interrupted.
Yeah,
So
and
continuous heat
my
source.
question is how much maximum temperature you can able to get it in the solar parabolic
Uh, so that 400 to 500 temperatures, sir. So like
Yeah, that
high
is sufficient
concentration
for this
ratio.
chemical reformation actually.
Okay, sir.
That is okay. For that region, this copper zinc oxide is the best electrocat. I mean, catalyst material for the reformer.
Sir, suppose if I maintain throughout that day, is the temperature range, so I can able to continuously produce that hydrogen, right?
Yeah. You can produce that.
Okay, sir. Thank you, sir. Any queries from participant sides? Any others?
There is some query from how to conduct life cycle assessment for hydrogen fuel cell actually. As I said, that life cycle as of now, this electrolysis process, depending on the type of electrolyzer which you are choosing. In the case of alkaline, it is about 30,000 hours has been proven. In the case of PEM-based electrolysis process, it's about 10,000 hours actually. And in the case of fuel cell, stationary, it's about 40,000 hours, and the transport, it will be about 5,000 hours. So you need to have a proper durability study has to be carried out at a constant power mode, and then you find out the decay rate actually. So that way you can make a life cycle assessment for the hydrogen fuel cell system.
Okay. Any others? Why storage is a very big challenge, sir? There is a query from participant side.
Yeah, actually, the storage, because the hydrogen has a light weight, the density is very low. So because of the low density, if you want to carry more mass, it occupies huge volume actually. So 50 liter hydrogen you want to carry, then the container capacity should be 50 liters. So at atmospheric pressure. But the mileage of hydrogen, if you use in best energy conversion medium like through fuel cell, 1 kg can handle about 50 to 45 to 50 kilometers. So if you want to cover 400 kilometers or 500 meters range, you have to carry more hydrogen. So it requires 6 kg. 6 kg is nothing but about 6 into 11 meter cube. There is 66 meter cube of hydrogen you have to carry on the board at atmospheric pressure. That is not possible. So you have to compress the hydrogen at elevated pressure. So if you want to compress the hydrogen at elevated pressure of 700 bar, then you need to have a proper storage cylinder material. So right now, the storage cylinder material, carbon composite material technology, which is not available right now in India, but there are a lot of R&D efforts are going on. But in the developed country, it is available. So you have to store the hydrogen at elevated pressure of 700 bar with a carbon composite material. Then only these fuel cell buses, fuel cell based, hydrogen based vehicles will be possible actually. So because of the low density of hydrogen, the storage is the major issue actually.
Okay, sir.
So there is another question in the same line of how to implement the vehicle. So I hope I have answered the question also. Basically, if you have a proper storage mechanism at elevated pressure, then the hydrogen vehicle implementation will be the easiest way actually.
Okay. I hope everyone is clear from our insight, sir. So, so thank you, sir. I am delighted to extend our heartfelt thanks to our esteemed resource person for delivering such an engaging and insightful session on advanced technologies for hydrogen production. Your comprehensive overview of cutting-edge methods, including electrolysis and innovative catalysis process, has greatly enhanced our understanding of hydrogen's role as a clean and sustainable energy source. The practical insights you shared on the challenges and opportunities in hydrogen production, along with the real-world application, were both provoking and inspiring. This session has provided valuable knowledge for those exploring sustainable energy solutions. Thank you once again for your time, expertise, and valuable contribution. We look forward to more such enriching sessions in the future. Thank you, sir. Thank you so much.
Thank you, thank you.
Is Sir, Dr. Subramanian, sir, is there any
Yeah.
insights from your side?
Thank you, sir. Thank you, sir, for delivering such an engaging and insightful session on green hydrogen production technologies. I think, as you highlighted already, green hydrogen is actually cornerstone in our transition to a sustainable and carbon neutral energy future. The advancements and challenges you shared today are not just technical, but also opportunities for collaboration and innovation in addressing global energy needs. I believe this session has been truly inspiring, offering us valuable knowledge and sparking ideas for how we can contribute to this growing field. Thank you, sir, once again. On behalf of Amizar College of Engineering, I sincerely thank you for sharing your expertise with us today. Thank you so much, sir.
Thank you, thank you.
Sir, kindly hold for a few seconds, sir, so we will take some snaps of
Yeah,
dear audience, can you switch on your video so that we can take some screenshots? Yeah, my job is done. Thank you so much, sir. So you can sign up that session.
Thank you.
Okay, thank you. Thank you all.
Thank you.
Thank you. Maybe we can conclude the session.
Okay, sir. So dear audience, thank you for your kind cooperation. So I hope everyone is enjoyed these sessions. So you got some valuable insights from the experts. So tomorrow also we are engaging this kind of expert sessions will be there. So the session, first session, we handled Dr. Bonu Prakash. He is actually that power electronic engineer from Idea Post Technologies. He is a senior manager in that particular company. So afterwards, af- af- afterwards, hello? Yeah. Afterward, there is another valuable session will be there with Dr. E. Anil Kumar Garu for what are the techniques are available for storing that hydrogen. So these two sessions will be very helpful for you for to continue your research journey in the field of sustainable energy. So I hope please be on time in that login schedule so that we can and kindly cooperate with us. And thank you. You can sign off your sessions.